Hello. This is the voice in your head. How are you doing today? Have you had your coffee? Are you being a good boy? Yes. Yes, you are. How do you know that you're being a good boy, though? You could be a bad boy. You could be a naughty boy. The summer is magic, Whoa. Is everyone ready to write some code today? Press 1 if you're ready to write some code today. Whoa, the summer's magic. Pick a better HDL first. Maybe you should stop suggesting your stupid shit. Ba-da-da-ba, skoo-doo-da-ba-ba, skababa, skabada, be-dee-da-ba-dee. You think we have a working bot in this chat? Oh. See, if my fans were more dedicated, they'd write me a bot, you know? New mail has arrived. That's not the personal delivery I was looking for. The personal PC specs would be way out of date anyway. Yeah. I kind of want to go hunt something. What can we go hunt, chat? F in the chat for the bot. Oh, look at that crown shield. Let's go. That's big. Oh, look at that. Big shield upgrade. Oh, it's heavier? That sucks. Yeah, but... Are we going to be able to get our code to work today, or is it going to be impossible? Thanks. Okay, let's do that. Where are we gonna put you, chat? Where's somewhere I don't read or care about? Because that's where I want to put chat. Let's see. Okay. Boom, 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 boom. How do I hack? First, you must install a virus. There you go. Boom, boom. Why are people responding with a smirk cat? Is this a smirk cat sort of stream? What does this even mean? The fuck does this mean? No, don't add more. You guys suck. Zed has been good to me. What's Zed? Zed is Z IDE. The editor. Oh, it has a side panel. I can't handle it. Oh God, aren't these all fucking like Zoomer ass companies? Adversarial robustness research lead. Oh my God. That's definitely not chat. You guys aren't robust as shit. Fucking nerds. Okay. Today we're gonna be doing some work on a FPGA. FPGA? G or J? FPGA? FPGA? I think it's FPGA. 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 Can we get our FPGAs in chat? Can someone make me a FPGA emoji? FPGA. Okay. FPGA. Okay, how do we turn this into a FPGA? Can AI do this yet? Do I have any good AI? Let's see. Let's clear my AI history so you don't see the sketchy ass shit that I look up, you know? Settings. How do I get rid of chats? Delete all. Yes. Okay. It's safe. Okay. How can I use this to make anything? Can I do any of these generate images? I don't think so. Open web UI image generation. Aren't these all online things? Can I do it offline? It's bad. Okay, we can't do that then. Yeah, can someone make a FPGA? I'll send you nothing in return. I don't even know what a FPGA would look like. Surely some of you do art or something. What would FPGA even look like? I don't know. That's why artistic ability is so valuable. Oh, we gotta go to chat. Zoom levels. Okay, is there anything else we need, chat? Oh my God, how are there 170 people here? What the fuck? Are you all bots? Press 1 in chat if you're a bot. Press 2 if you're not a bot. What's our chat latency? It's not that bad right now. They want you to use a different... You're the only person saying that! You're the only one who cares! You're the only one here who gives a shit about the Hiddle. Scarlet Berry? I like that name. I like Scarlet Berry. I think that's a pretty good name for a chatter. Maybe I'm the only one who knows the Verilog spec. Yeah, and I know the C spec. You don't see me advocating against C. I love the undefined behavior. Oh no. Why does my sound system pick up the GSM tones so easily? I don't know where it's so leaky. I don't know if it's like USB grounding. I have no idea. Okay, chat. So today we're going to be making a Linux kernel. Probably not first. We're going to try and write to memory from the FPGA. So if my FPGA is able to boot into Linux, if I just change these pins, let me go see what I have to change them to. What's our DE10? 1010. We need to go to 100. Nope, no. We want 01010. 01010. S'mores, watch out, Bubbis. 01010. 01010. Okay, so, and then I'm going to power cycle my FPGA. And what this should do is it should just boot into Linux with like full HDMI, 1 gigabit Ethernet. It boots pretty fast, so I just plugged it in. And this should just come through. There we go. So that's like bootloader, go right into Linux. And then we pop into XFCE. And there we go. That's a pretty good setup. So this is running off of an SD card that came with it. It came with that 32 gig Team Group SD card, which is actually a pretty good micro SD card. Where's my desktop? But the issue with this setup is I'm pretty sure it flashes the FPGA with some necessary components, I think, to get Ethernet working and the frame buffer working, because the HDMI controller is actually connected to the FPGA. So to be able to use HDMI, you need some code uploaded to the FPGA for the Linux kernel to be able to display things. So I don't know why the desktop isn't showing up. Let's reboot it. Actually, there's a reset button. Not that I really care about going into XFCE. I also have a terminal over like a UART over USB, so it's just got a USB mini. Yeah, there we go. So normally the background loads. I don't know why. Oh, there we go. So there's like a full XFCE desktop. So out of the box with the SD card and those switches set to the right position, it just boots into this. So either U-boot or the kernel flashes the FPGA with basically the hardware requirements to get like HDMI and Ethernet working and maybe some other things. I'm not 100% sure. The downside of this environment is it's not easy to do rapid development on the FPGA, because if I were to go and flash the FPGA right now, like if I were to use the programmer and actually send down a new FPGA program, Linux, I'm pretty sure it just reboots or like goes unresponsive or something. And that's because Linux is relying on some existing programming and state in that FPGA. So what I want to do today is I want to fully decouple the FPGA from the system on a chip. So the system on a chip, or the HPS is what they call it, the hard processor something, just hard processor. I'll probably say SOC. I'll try and say HPS. But effectively, there's an ARM processor, there's a gig of RAM, and there's a bunch of peripherals. And we can pull up the mapping. I think the manual has a pretty good mapping of what goes to what. This kind of does. I feel like there's a better block diagram somewhere, though. Not 100% sure. There might be a quick start manual. Let me see. Because I got like a sheet of paper that was really nice when I spot it. Quick start guide? Is it this? Yeah. Okay, so this kind of maps out how things are connected, so you can tell by the different colors whether something goes to the FPGA or whether it goes to the ARM processor. So this kind of is a way to know like what's connected to what. So my view is that we should be able to decouple the ARM processor and the FPGA entirely such that we can constantly reprogram new applications down to the FPGA while Linux just stays running completely fine on the actual processor. So the ideal goal is that we're going to be doing like FPGA rapid development where we're just pushing it down with the programmer over JTAG, and the hard processor will just stay running Linux. Everything will be fine. So we can basically do all of our testing on the FPGA because the Linux code is going to be really easy to get right. It's fucking trivial. We're going to map in some memory from devmem and just read and write memory. It's going to be the easiest code on the planet. The FPGA is going to be the hard part that we're going to need to debug and like try more stuff on. So, we'll go through this board a little bit. Let me check up on chat. The C spec is super great compared to Verilog. Oh god. I used to be able to know when a call was coming because my phone sat on my subwoofer and it would start making noise before the call rang. Yeah. So Grand Theft Auto 4 intentionally added that before phone calls, and I thought that was always a really cool taste for like a video game to have. Holy shit, we're over 200 viewers. What the fuck? This is a Cyclone 5. Yeah, so this is the dev board that we have. It's a DE10 Nano, which is running an Altera, or now Intel Cyclone 5, which is kind of a low-end FPGA, but it's, for anything I would do, this is actually a pretty good FPGA. It's probably got like 10 times more logic elements than like kind of the cheapest FPGA you can get. So this is a really cool system. But yeah, this is the board. So we have the power jack here, which it came with a little barrel connector to run the power on it. You have the USB blaster. So this is a JTAG USB thing. So I have, when I program it, right, when I hit the start button here, it's going to run JTAG to the hard processor and the FPGA, and this allows me to basically program those, and in theory, I should be able to, like, JTAG single step the processor and, like, do all sorts of things. Then there's, HDMI output, which I have hooked up. That's displaying this desktop here. What else do I have? It has a USB on-the-go connector. If you're not familiar with on-the-go just means that you can have this port behave as either a host or a device. So I can either plug in a peripheral here, like a USB drive or something like that, and it will show up to Linux as a USB drive. But I can also use this same port to host a USB device, or like have this board behave as a USB device, so I could plug this FPGA board into another computer and it would show up as a keyboard or a mouse or, you know, whatever I program it to be. Then there's the UART output. This just has like a standard FTDI. That's what I have hooked up to get the like Linux shell, and that's mainly what we're going to be working on. But what we really care about is the colors of the different components here. So anything that's in this like orange color means that it's connected to the hard processor. So here we can see that the UART is hooked up to the hard processor. So is the Ethernet. Apparently, I didn't know that. This like warm reset and HPS reset, these buttons allow me to like reboot the system. It's like the reboot button on your actual computer. But these other buttons and switches and GPIOs go to the FPGA. So what's really cool about this diagram is it kind of tells me what I should, in theory, be able to run without the FPGA at all. So from this, I should be able to run code on the ARM processor. It should have access to the 1 gig of DDR3. It should have access to the USB port. It should have access to the UART, to Ethernet, so on and so forth, and the micro SD card. So all of those things should be hard connected to the ARM part of the system. But there are things, I really think it's just the HDMI. The HDMI is hooked up to the FPGA. So if we want to use HDMI output from the ARM processor, we would need to flash some code onto the FPGA that allows basically transmitting whatever frame buffer format from a Linux driver that's aware of that frame buffer. The FPGA has to pull that out of memory and blast it to the actual HDMI port. So what we're going to be doing today will not work with HDMI output, because we want to have full control of the FPGA as a separate thing entirely from the processor. So that's the goal. Does that make sense? That way we can do rapid prototyping on the FPGA, constantly flash things down. We don't have to worry about interrupting Linux if we want to also like keep that up and running. So what we can do is we can go back into the other mode. So right now it's in a mode where when I boot this board, it's going to boot the SoC. It's not going to program the FPGA, but what it's going to do is Linux is actually going to program the FPGA as part of its boot sequence. So instead, I'm going to actually put it into EPCS mode, which means that the programming of the FPGA is actually done by a flash chip on board, and we can override it by directly writing it with the programmer and using JTAG. So we're going to switch over into that mode now, and it will still boot on the SoC, but the SoC isn't going to be able to program the FPGA, so we're going to see that it's going to fail to boot. So let me make those switch changes. Let me go look them up. 1010. So we're going to go into this EPCS mode, which is 10010. Okay, and now I'll just power cycle the board. And what we'll see is that this is going to fail to boot. And it's because it's not able to program the FPGA. So I think U-boot programs the FPGA first, and then Linux also tries to program it. So you can see that it's just failing to boot. So like a lot of things are just not correctly set up in this environment. Linux is like, some things are hard-coded that are expecting to be able to program it, so on and so forth. Yeah, it's just a mess. And then we drop into the U-boot shell. So instead what I'll do, the FPGA is completely unprogrammed right now, so I can flash on my little program right now, which is going to make some LEDs show up for me. And I can see that it's fully functioning. The FPGA is working as if this board only has an FPGA on it. Then, I can reset the SoC, and this does not affect the FPGA at all. So the FPGA still has the same state. It's just been running the whole time. But you can see that I can drop into this U-boot shell. So we have a fully functioning U-boot environment over the UART, completely separate from the FPGA. This has set up like RAM and everything, so I can dump memory. So in theory, this system should be able to boot Linux. So I made some notes here on how I can kind of manually load this kernel. So what we're going to do is we're going to load the DTB, which is the device tree. It basically describes the layout of memory and devices for Linux. And then we can load the Z image. This is the actual Linux kernel image into their respective addresses. And then we can use a boot Z command, which is then going to boot from RAM. It's going to boot this ZM image at this address. It's going to use dash as the RAM disk. In this case, we don't have a RAM disk, so dash means no RAM disk. And then we give it the address of the device tree so that Linux knows the layout of the system. And this boots into Linux. So there we go. We have the FPGA completely separate from this. So the FPGA is still running my program. The LEDs are still there. The state is maintained. But we're able to boot functioning Linux. Now, obviously, it's failing because of not having a root partition set up. But my view is that if you fail to boot Linux because it's not able to find the root partition, this is a pretty deep boot, in my opinion. If you can get this far, it means RAM is working. It means that your UART is working. Like the actual transition into Linux is working. It has timers, it has interrupts working. Like, getting this far in the boot process pretty much means that Linux is good to go. So all we need to do is we need to basically put a root boot option on this. So I actually made a save over on a different screen. I saved off all of the environment variables from U-boot. So in U-boot, you can just type env, like it's a Linux shell, and it will dump all the environment variables. So we can kind of take a look at like what by default they have. And just kind of look at like how they program things, what sorts of things they're doing in here. Here we can see like HDMI enabled, I guess that's specifically DVI. We can see that it like, I think boot command is what it runs. So we can see that boot command, like the default thing that it will do without dropping into the shell by hitting a key to escape the boot process. It's going to configure the FPGA, it's going to initialize HDMI, it's then going to boot the distro, and that is doing, it's going through all the boot targets, and then it's running the boot command for that target, and I think that's where it will end up dropping into Linux and everything. But we can see that there's like other interesting commands here, just miscellaneous things in here. So effectively what we need to do is we should be able to just give it a root boot option. What's really cool is we can see the partitions. So like Linux is able to talk to this MMC and everything without the FPGA. That's fantastic. I'm pretty sure this partition is Linux. So the first one's the like boot partition. Then we have a Linux partition, and then finally we have I forget what this is. I think it's just like a custom partition. And we can see that with like MMC, I made a note of it. MMC part lists all the partitions. So this is all the partitions on the SD card. We have the boot partition, we have the Linux root, and we have this A2, which I think is just custom partition or something. And we can do an ls of the MMC device, the MMC device 0, and then partition 1. So here we can see the layout of the boot partition. Super simple. We can see the kernel, the Linux kernel Z image. We can see the DTB file for this system. We can see this RBF file. The RBF file is the FPGA code. So this is what it would flash onto the FPGA. Like by default, U-boot would flash this. License info, I'm pretty sure that's just a license file. Haven't actually looked at the contents. HDMI configuration, the EDID, and the registers. That's all HDMI related. Startup.bmp, I imagine that's literally just that boot splash screen that you see. And that's about it. So really, all we care about to boot Linux is the Z image and the DTB. There is no init RAMFS, at least that I see in here, so I just assume there isn't one. Typically, if you're using like an MMC device, you're probably not going to need an init RAMFS because that driver is going to be baked into the kernel. Obviously, depends on how you make the system. And then we can also dump 02. This is the ext2fs. This is the actual Linux file system. So super simple there. So obviously that's working totally fine. So let's go and change the boot command for the system. And hopefully we can get in. So boot args currently is console TTY S0 115200. So use telling Linux to use the 0th serial port at 115200 baud as the boot console. So what we'll do is we'll load these MMC commands. So this is going to be loading. Now this is loading from MMC device 0, partition 1, it is loading this DTB file. So that's all it's doing. It's loading this file into RAM at this address, which happens to be FDT adder R, right? I don't know how these variables were set, but they were set by default. I imagine it's just baked into some setting stuff because I'm pretty sure that you can change environment variables. So we'll look into that. Maybe we can persist these commands. I'm not sure if that requires reflashing or if you can do that directly from the shell, but I think you can do it from the shell. So then the next thing we need to do is we need to change the, what is it, boot args? Yep. We're going to... How do you think I change those? Is it just set? Oh, yeah. Here we go. Save environment. Okay, so you can save them to persistent storage. Is the stream going to be uploaded to YouTube? Yeah, we can. We can do that. SoC and FPGA are on the same chip. Yeah, it's a really cool board. I think this board was like $200. Pretty cheap. Set env, variable boot args, and then I imagine that we should re-specify these. I imagine it's going to overwrite them, and we'll put it in single ticks. And then root is equal to, what did it tell me? So usually when you have this issue, you just grab the actual partition that you want because the kernel will just dump out what it can see. So this is partition 2 on MMC block 0. So let's just do dev this. Uh-oh, that didn't work. Okay, let's see if we're not supposed to put ticks. Don't run save env after. Okay, yeah, I imagine that's to persist it. I vastly prefer Xilinx ecosystem. Yeah, I've heard it's way better. Unfortunately, this board, first of all, I just love these DEO, D10 boards. I have a DEO Nano from like 10 years ago. It's just a beautiful board. I love the like the clear plastic cover on it. It's just a really sleek board. I don't know. I just really like their stuff, and their documentation is good. It's a Taiwanese company, or Chinese if you're Chinese. Shout out to Xi, big fan. So basically, their documentation is always really good. They ship out like an ISO that has everything you want on it. They're good about giving you all of the software, all of the code in an environment that you can build, all of the components, the bootloaders, the kernel, everything. I don't know. I like their documentation. It's really good. I'm sure there are Xilinx boards that are similar, but I don't know. I'm sure the FPGA dev environment, like Quartus, just sucks ass. I know Vivado recently got updated. I think that used to suck, but I think Vivado is the new rewrite that I think has been a big improvement for that ecosystem. Yeah. I've heard good things. So, personally, I think what we're going to be doing is so light that it hopefully just doesn't really matter. Okay, why can't we do this set env? What are we doing wrong? Help, set env. Help. What have we done? Wait. Am I in the shell? What am I in? Oh, yeah, I'm multi-line. Okay. Woo! Woo! P2. Echo boot args. Okay, so this, in theory, I think we already loaded the stuff into RAM. This, in theory, I think is going to just boot into Linux. I'm not 100% sure if this is going to get mad because there's no HID-DIMMY. Hopefully it can just fail open. Yeah, there we go. We got system D. Okay, yep, we're crashing in LED probe because there is a driver that's trying to use the LED devices, the and that's not programmed in. But basically, this is a fully booting system. This is totally fine. If you get to system D, it's GG. So it's trying to start XFCE, all that sort of thing. So, what do you want to do first, chat? Do you want to try and do some FPGA work, or do you want to try and build a Linux kernel that we can boot? I'm not sure how hard it is to build this kernel. I wonder if I can build just latest Linux for this, or if I have to use their specific flavor. I'm pretty sure that they have an SD card image that is a little bit more stripped down than the XFCE one. So that's another option. And yeah, we rebooted. Try restarting the FPGA with Linux still up? Yeah, I can program the FPGA. It's totally fine. It doesn't affect anything. Yeah, like, They are completely separate. There's nothing is joined here, which is nice. So but basically my view is that we don't actually need Linux yet. Obviously Linux is it's just going to work, right? Like, this is just a matter of either building a new kernel or just changing this to, like, not use these drivers or expect these things. Like, this is trivial. This is a fully booted system. Everything's working. RAM's working. Disk is working. It's getting to system D, like, and it's running. That's a solved problem. That's not an issue at all. So, getting Linux to work is a trivial amount of work. So, I kind of just don't care about Linux until we actually get an example program running, because there's really good abilities to dump memory through is it MD or tu y yo a la fiesta, tu y yo toda la noche. Is it MD? So I can dump bytes at a given address, right? And I can say, I want 1024 bytes at an address, right? And this is dumping physical memory. So my view is that this environment should be totally fine. I think at C0001234, I think this is that rebooting us? Okay, we froze. So I'm pretty sure that is where this is the location where the FPGA should be able to access things. Not 100% sure, but I think there's 512 megs of RAM that should be accessible at this bridge. I saw some things about the bridge. Let me see. Bridge. Help bridge. Is it disabled by default? That's what I'm curious about. Bridge enabled. Does this work? Because now can I dump this? MD. Let's just dump 1, 2, 3, 1, 2, 3, 4, and dump 4. Okay, so that still freezes. I'm not 100% sure. But my view is, like, we can read and write physical memory from U-boot, so we don't need to be running Linux. Obviously, once we're in Linux, you just open devmem. It's the same fucking thing. The Linux side of this software is going to be so easy. I just don't even care. So yeah, I'm not 100% sure on how we write memory. So what I want to do is I've got a really, really simple Verilog program. I have a module that basically is able to do the serial port conversation with the analog to digital converter that I've added to the system, and this works totally fine. I actually did a little bit improvement on this off stream. I was having issues with the version that we wrote off on stream. Let me rebuild this quick. Let's build this. Make sure we update this this output, and then let's load all our variables up so you can kind of see clock, CS, data, queued, then DRO, SPI, and this. Okay, so this is basically what we're using to read the analog to digital converter. So before, what we were doing is we were actually clocking the SPI bus, the SPI bus, when we drop chip select, and that was causing me, I think the chip was like seeing that, and it was a little bit of an issue. So instead, what I do now is the SPI clock is actually masked, and I've doubled the clock rate of the actual clock going into Verilog. That allows me to basically simulate doing work on the rising and falling edges. So now, instead of being an 18 cycle loop, it's now a 17 cycle loop, because I was able to have up front and at the end. So basically we enabled a chip, and then one clock cycle later, which is effectively the falling edge of our SPI clock, we then start issuing the SPI clocks. We do the 3 clocks that discard information, then the next 13 pull off the 13 bits from the ADC, and then we disable on another clock, so on like this half clock, so the falling edge of the SPI clock, we then disable the chip for the amount of time, for 2 cycles, or for 1 cycle, for 1 SPI clock cycle, but we also mask off that SPI clock. So this is a much cleaner circuit, in my opinion, or like driver, and this works totally fine. It fixes the issue where we were shifting over one too far, which is, I think we were picking up one of these clock edges was actually consuming a bit. So now everything works. This is a better implementation, in my opinion. Everything's nice and clean and isolated and works fantastic. We're getting full 100.0 kilohertz kilosamples per second from that ADC. So, anyways, that's the changes we made to the ADC when I was offline. And other than that, now what I want to do is I want to look at that ADC data. I haven't been able to work at it. Board info on U-boot should show where memory is. Board info? That? Help? Board? Board info? Help. Board info on U-boot should show... Looks like GTK wave. This is Surfer. It's fantastic. It's really good. How's everyone doing? Fantastic. It's been a while since live streams. Yeah, we did one a couple days ago. But this is yeah, I should also advertise that we're streaming on Twitter. God, I hope I'm logged in. My verification code. Let's hope I have 2-factor set up on this phone. Twitter. Uh-oh, I have 2 Twitter entries. Oh, shit. First fucking try, let's go. Okay, I need to remove this one. How do I remove this? Whatever. Doesn't matter. Okay, let's advertise this on Twitter. Live doing some FPGA and Linux dev, HPS twitch.tv/Gamozo. That's us. There we go. We've twinted. First time I gotta learn in a while, yeah. What's Twitter? Is it something like X? I spent the whole day fighting Ghidra? Yeah. Yeah, at this point, like, I just have all reverse engineering tools, and I just keep opening my software until one of them works, because, like, most of them will not work out of the box. I'm wanting to self-host my cloud. Driving photo services plus privacy enhancing services. Mini PC N100 or a full-size desktop with i5. So what I do, whenever I want to run a new service in my house, I buy one of the, like super micro, one-use system, like the Atom machines. Yeah, like one of these. They make like a couple different ones. You can get them like somewhere between like $500 and like $1,000. You can get them spec'd out pretty nice. Yeah, like this is a 24 core. Like this is pretty nuts. This is old though, I think. Yeah, this looks old. They have a bunch of these, but I can get them in like 2 days. Throw an NVMe drive in it for $100, and like now you have a nice 1U you can set aside for a specific task. You get the Lathe refined? Not yet. We're, right now, the software that we're writing... I'm not listening to these fucking random DJs. Right now, this is part of the Lathe project. So what we're doing right now is for that. Okay, let's see. What do we want to listen to today? We're going emo. Leaning towards emo right now. Let's, is this album any good? I think this album's okay. Let's try this. FPGA CPU for the Lathe project. We're deep in the hole. Yeah. Right now we're like 8 levels deep in the stack. Because this project is for the milling machine. And I've been working on a fixture jig for sharpening the carbide blades for scraping the lathe. And I'm trying to make a like fairly complex geometry for the blades. And I want it like really repeatable. So I'm just making these like little carriers. Let me show this project. The fuck is this? FreeCAD. This should work. So basically this is what I am building. So I'm building this little holder that will hold the carbide blank here. And it's going to make a pretty complicated geometry on this blade because this blade has a, like this radius, I think this is a 20 millimeter radius is this curve. And then these corners have like a really tight radius. So typically what you do when you're scraping is you'll have a blade that is, it's just this radius to the end. And then you'll have a sharp square corner. The problem is when you're using a really small blade like this is a 13 millimeter blade. When you're using a really small blade, it's very, very easy for you to kind of dip one of these corners and you're going to just put a massive gouge in your part. So what I want to do is I want to be able to put these like really cute relief corners on here. So we have this like really tight corner here that should hopefully allow me to dip this. And yes, this would put a deeper groove in the part. This shouldn't cause like a really deep scratch that you effectively could never get rid of with scraping, because the scratch that you'd put in with a sharp corner of this blade, it's deep. It's probably like almost I don't know, like a maybe 0.1 of a millimeter deep, which is hopefully a lot deeper than the amount of material that you're going to remove during the scraping process. So it's a pretty big amount of damage. So I've decided to make this like carrier setup. I don't know where my like, there's my model. And let's see, this is just this carrier. So this carrier is quite small. For reference, these screws, these are M2 screws, so 2 millimeter screws. And this is kind of the smallest machining project I've ever done. So to drill for these holes, I need to drill like a 1.6 millimeter hole, and I am intentionally making this part out of 316 stainless steel, and 316 stainless is a pretty difficult material to work with, especially for like drilling and tapping. So this is just a really fun project to work with these really small holes, and these are, I think these are 1.5 millimeter holes, and these chamfers are very, very tiny on these. But effectively, the design of this is that I will put the blade in here, and then this kind of whole board is mirrored with these 3 holes. You see these 3 holes on each side. So I put in the carbide blank, I clamp it down in this fixture, and then these holes allow me to put in different pins. And this pin is set up to be 20 millimeters from the edge of this blade, so that will make the 20 millimeter radius, the large radius here. And then these pins will allow me to make these corners, right? So these have a much, much smaller radius. I think these have like a 2 millimeter radius, so the distance between this and the edge of the blade that you'll end up making, that's a very, very tight corner. But what I can do is I can take this, and I'm building a base like this. I've already actually made this part, and this base is on a 5-degree angle because the blade will have a 5-degree angle, will be the actual acting edge of the blade. And then up top here, I have 20, 40, 60, 80, or a 90, and a 140 for different holes. And then you can see the corresponding for the corner radius for the different size holders. So basically what I'll do is I'll put in a pin here, and then the little holder will sit in that pin, rotate around here, and then I'll just have a grinding wheel over here grinding the edge. And then when I'm done making the main cutter edge, I can then put a pin in here, and now I can make the corner for each side. So effectively it allows me to probably within like easily 10 micron grind the exact same geometry on the blade, and then I flip the entire carrier over, repeat the process, and I'll have two very nice edges on a blade. And then effectively I just have to build different holders for the different radius, different radii blades. So I'll make a couple of these different holders. Anyways, the project we're working on right now is just kind of part of improving the automation on my milling machine, such that I can dial in like much more precise movements of the X, Y, and Z axes. So right now, the digital readout that I have just tells me the position in X, Y, and Z space, but it doesn't actually tell me the speed of the movement, and the speed that you're moving the tool when you're machining a part matters a lot. And right now, I just kind of have a lookup table that I have written down on a notepad where I go into that, and I literally just read my notes for like what setting from 1 to 10 on the potentiometer I use for different speeds. But what I'd really like to be able to do is dial in like much finer than that. For example, if I'm drilling a hole, when drilling these really small holes, I don't really get good feedback on the quill, so I'd rather do like power feeding, just directly drilling like with the Z-axis feed. The issue with the spindle on the Bridgeport is the spindle has 3 different down feed speeds. It has 1.5 thousandths of an inch per revolution, 3 thousandths, and 6 thousandths. And when you're drilling holes under like 2 or 3 millimeters, you kind of need to go under 1.5 thousandths of an inch per revolution. So effectively, I'm feeding the drill bit too quickly into the part. And so what I'd really like to be able to do is get an idea of how fast the machine is traveling on the digital readout. So effectively use a timer or a clock in the digital readout and just display in real time, like at the 60 hertz refresh rate of a screen, tell me the actual movement speeds of the X, Y, and Z axis. And then I can dial in, I imagine I could dial in very precise movement speeds. And then I don't have to have my lookup table, which is going to be incorrect when, like, I put a heavier part on the table and that's causing the motors to bog down more, which causes the X, Y, and Z's to move at different speeds. So that's what I want to do. And to do that, I want to directly actually build my own DRO that will use ADCs to read the signal that is put out by the linear scales that actually tell me the positioning. And then in software, I can do whatever I want. In software, in Linux, I'll have real-time information about the positioning of the X, Y, and Z axis. And effectively, I can just write different software to use that data if I want to graph it out or like actually feed it back and like use a stepper motor. Then I could make a CNC machine. I could add like a sensor onto the spindle, and now I have RPM and X, Y, and Z. I could add readout for the quill, and then I'd have X, Y, Z, RPM, and quill down feed, and it would like there's just a lot of flexibility where I can just like add more and more sensors. I'm never gonna run out of GPIOs on a system like this. And I think that just, I don't know. It's like a 4-inch by 2-inch dev board, and that's all I need to like run this entire setup. I can power the scales. They're very low power. I can run them directly off the board. I don't need a separate power supply. I just think this is gonna be a really cool setup, and then I'll just make a little enclosure, hook it up to a screen, and now I have Linux with a GUI, and then I can use an FPGA to do like signal processing or like real-time buffering. So instead of having to have Linux like constantly polling the ADC, I can instead have the FPGA just dumping like every 50 milliseconds, just dump the readings to a memory map file, and then have Linux just wake up and read those every once in a while. So like I can make things a lot lighter on the Linux side. And like I was talking about in the other stream, these scales are relative scales. They are not absolute scales. So if you ever had like a Linux like micro stutter and that causes you to miss an ADC reading, the scales will be permanently off. Permanently in terms, the reading will be inaccurate, because if you miss a movement of the scale, since you're measuring only relative movements, if you miss a movement once, you permanently have the scale now off, and that will cause you to damage parts, whatever. So that's really the reason I want to use the FPGA. Obviously, like a microcontroller with a custom operating system would be totally fine, because that will be real-time enough, and you would never really miss something like reading the ADC. But in Linux, I don't really trust it. So this way we can have the FPGA recording all that data and then shipping it over to Linux, and Linux can then process it. We can write like a PyQt application for the actual DRO GUI and interface and all those sorts of things, like a standard keyboard and mouse setup, because with a custom OS, making a good interface is going to suck. It just will. So we will eventually need to figure out how to get HDMI output working with our custom FPGA software, but I think that's pretty easy. I think as long as you're letting Linux write the FPGA programming on, I think that's actually not too bad. But right now during development and rapid prototyping, I really don't want to have to, part of the development loop is like remove the SD card, plug it into my machine, mount it, write a file into overwrite the programming, remove the SD card from my desktop, plug it back into the board, reboot the board, let it boot into Linux with a GUI, and then like run my application and see if what we dev'd worked, and if it didn't, restart that process. So instead, what I want to do is just be able to rapid prototype on the FPGA. And really, I'm already at the point where I get the sensor readings, and I output. I have a 13-bit ADC, and on the LEDs on the dev board, I output like the top 8 bits of that. And I've done some calibration testing against other reference voltages, and ADC is working great. Everything's good within spec, behaving fantastic. So now what we need to do is, I want to look at this data more than just seeing it on LEDs. In fact, I have never looked at how these scales behave on both phases. So this scale outputs 2 sine waves, and the sine waves are 90 degrees apart in phase. And I've never gotten to look at what the signals look like together. So I can with my oscilloscope, but my oscilloscope has a really shitty ADC. It's just a cheap Rigol. It has like an 8-bit ADC. I have looked at the scale outputs on my multimeter, which allows me to do 16-bit ADCs at 1 meg sample a second. So I've been able to like graph that out, and I have those. We can close this. CD machining, linear scale scanned, and I think I can plot raw. Yeah, so this is the actual signal that I get out of the scale as I move it. And this is from my multimeter. This is probably at 1 million samples a second. And this will have 16 bits of resolution. So we can see kind of this sine wave. This is actually, this is phase A with respect to phase B. So this is actually both phases kind of combined together, and this is with clipping. That's why this waveform is not a clean waveform. One of the phases is always clipping here. But I've never gotten to look at both waveforms at the same time. With the FPGA, that should be really easy. I can just basically stream. I can set up multiple ADCs. I could set up. I bought 15 ADCs, so I could theoretically set up 15 ADCs, run them at 100 kilosamples per second, dump those to memory, and then in Linux, I can save those to disk or record them into memory into like a gig of RAM. I could store a shit ton of data, and then we can go and look at those waveforms, and they'll be like in lockstep. I can compare them. Effectively, what we're building is a 100 kilosample a second 13-bit oscilloscope, right? But what we need now is we need a place to store the data. We could store a little bit in the FPGA, like the FPGA, we could put some RAM on it, or we could use SRAM cells or like the memory bits that are built into the FPGA side of things. But that's not very good to interface with because, okay, now it's in RAM, what do? We shit it over UART to Linux. Like, that's not a great experience. So what we're going to try and do is get this writing directly into RAM that is accessible by Linux. And then hopefully we can just dump and read that information off. So I don't know how much work this is going to be. I don't know if we're going to have to start with like the big everything FPGA projects and then remove things to kind of minimize it down. Ideally, I can just add things to my existing really, really minimized program here. But yeah, that's what we're going to be doing. Let me check up on chat. Sorry I don't read chat. Not fun to machine. Yeah, 316 is a pain. But it's basically all that I've like worked with. There's an ideal load based on the material. Yeah, especially with small end mills. Yeah, the smaller the end mill, the more a lot of these feeds and speeds matter. And it's just really hard to dial that in, like, with these power feeds when I don't have a way of seeing the actual speed. Because I'm dialing in, like, probably 1 degree on the potentiometer because 90% of the potentiometer range is way too fast to use with these like really small drills and end mills. And for 316, the difficult part about 316 stainless is that it work hardens. So effectively, like wherever you're cutting, like when you're drilling, right where you're drilling, you're forming like a very, very hard layer. So if you do like the standard drilling process where you peck it and you put the drill in, you remove it to clear the chips, and you kind of go up and down like you would drill a lot of different metals, you're actually screwing yourself because when you exit and then come back in, you now have to go through a hard layer. You're going to heat up your drill bit. You're going to really hurt that edge of the drill bit. You're going to risk breakage. So with stainless, you kind of have to always stay under that hard surface. So once you get a cut going, you have to stay going. So I pretty much only ever drill stainless by using the power down feed of my Bridgeport, but unfortunately the Bridgeport power down feed is very weak, so you can't use it for large holes. So I'd like to be able to use the power Z axis for like large holes. I could then feed the entire Z into it, and what I could do is, since I have a VFD and I can see the RPM of the spindle, I'll be able to just dial in the RPM of the machine, and then I can, once I have this like FPGA software written, I can just dial in the vertical speed of my Z axis until I get the right like feed per RPM, just divide it by the RPM speed, and if I have that sensor, then it can just automatically display in real time what the down feed per revolution is, which would be amazing, and then I can just dial it in. And yeah, I have a potentiometer that's like unlabeled, but I don't care. I'll just change it until it matches what I want, and then bring the part up into it. My view is it will probably take like a couple seconds to just dial it into the right speeds. And this is going to help me with both small holes and large holes. Large holes because the existing power down feed cannot drill a large hole. It has like a clutch mechanism that is intentionally meant to trip if it notices too much force because it's designed for very, very light drilling. So I'll be able to drill large holes, and then on the opposite end of the spectrum, I'll be able to do small holes because I'll be able to dial in a vertical travel speed that is much slower than the like RPM per revolution that I can with the existing 3 gear settings on the mill. So this project really helps me with a lot of my machining projects. And it will also be cool just to be able to digitize the movements of the machining. Like, I can just record this data while I do machining, and I could use that to potentially view, like, how much load is on the machine, how much does it slow down when it actually is doing a cut versus when it's just traveling. Like, there's just a lot of information that would be kind of cool. And then, of course, that can lead into, we could rip out our milling screws on our milling table, put in ball screws, put in some servos or stepper motors, and then have this FPGA output to a like stepper motor driver board, and now we can do CNC, and we could do our own CNC software, which is something that I really want to do. I know I have to get into CNC. Unfortunately, you can just make so much more complex parts with CNC. Like, you can make round parts on a mill with a CNC. Obviously, you can do it manually, but you need to set up a rotary table and make sure everything's centered at the right axis, dial everything in. You do, like, one cut, and then CNC just has so many improvements there. But it would be really fun to write our own CNC software and then build a CNC machine. I'd love to build a CNC machine out of like a CNC grinder or like a CNC lathe that we build out of like granite parallels, or like I'd love to build a jig borer and jig grinder that are based on like granite slabs, and we could try and make a CNC machine that can hit like 1 micron accuracy reliably and do all the calibration and all of that work and all the programming ourselves. And I think that would just be a really fun project. So to do that, we need a way of doing positioning, and these scales are perfect for that. These scales go down to 100 nanometers of resolution, and they're accurate to within like 1 micrometer across the entire like 1 meter length of these scales. So in theory, we should be able to position things down to 1 micrometer accurately with these scales, but we can also get repeatability down to like 100 nanometers in terms of hitting the same spots based on the accuracy of the scales. But with good ADCs, we should be able to go under 100 nanometers. I think in theory we could probably go down to like 10 nanometers with this. It's really the quality of the ADCs, the quality of the power supplies. We could always maybe upgrade the sensor boards on this, like add stronger LEDs, improve their power filtering and reference power levels, so that maybe we could get more and more accuracy, because at the end of the day, the glass interference sine wave pattern, it's just a physical property. We should be able to nearly continuously improve that resolution by just increasing the quality of the signal that we get from it. Like, the physical construction of these scales is good enough to go down probably to 10 nanometers, which is really, really cool. My plan is to be using these scales on everything. So, like, this software needs to be nice and super extensible, because we'll use these for CNC projects. We'll use this for, like, making an electron microscope, positioning table, so we can know like where things are positioned. We can use that for feedback if we want to do like imagery of chips. There's so much shit that I want to do with these scales. These scales are basically going to be how I measure where things are in a 3D space on every single project, except for maybe ones where I'm using like an interferometer. So let's see. Is there an interesting update or data regarding S-Lang? There isn't yet. I haven't really started any dev on it. I started some dev on the IDE, and then I've kind of decided that I want to like maybe prototype out a syntax for the language, write a parser for it, because my view is that I can just start basically with C, and I want to implement features that I know that I will always want in the language, and then I could write the language in that. So like we could start with effectively just making a C compiler, and then we can start writing the language in itself, as long as we don't do major syntax changes that would cause us to have to rewrite major components and stuff. So really what I want to do is just start with like the base design of the language, which is just going to basically be C. Everything on top of that's just going to be like syntax sugar, in my opinion. I don't know. I really would like to be able to write stuff in it soon. I don't know. I'm just kind of sick of writing Rust. Like, yeah, we'll see. This D10 Nano board looks pretty sick. Yeah, it's fantastic. I really love this board. $200, Giga RAM, 800 megahertz dual core ARM processor. I think it's a dual core. It might be single. I think it's dual. Like, quite a powerful board. And the FPGA is also a pretty large FPGA in the grand scheme of things. So, I don't know. And the boot times are fantastic. Like, look how fast we can get a shell, right? I'm gonna hit reset. 3, 2, 1, reset. And there you go. We're in a shell. So, like, I would say it's probably sub 100 nanoseconds to get, or 100 milliseconds to drop into the U-boot shell. We probably can get Linux to boot within a second. I imagine we could probably get Linux under 100 milliseconds. Probably not with like systemd, but with a custom init program. I don't know. Like, it's really cool. I didn't think I'd be able to keep the ARM processor completely disjoint from the FPGA. I thought they'd be more intertwined. I didn't think we'd be able to boot Linux without programming the FPGA with some connective circuitry, but nope, we can keep them separate, which is really cool. Love this. Okay, so basically what we want to do is find a way to get data from the FPGA over to the processor. That's it. Really ideally I'd like to do it in memory, so I want to be able to write to memory that I can dump from Linux or maybe this U-boot shell. I don't know if I need to like boot into Linux to have Linux initialize some of the stuff. I'm not 100% sure. Let's see. Let's try and boot into Linux so we could maybe get like IOMEM and maybe like view a mapping of the system. But unfortunately, this image just might not boot correctly. I need the setenv boot args consoles ttys 015200, and then we want root equals dev. Where was it? Here. MMC block 0. So let's make note of this. And then we should be able to set args. Let's see if we can persist these. Yeah, maybe let's do a little bit of Linux first, just in case Linux needs to initialize some stuff, because we're going to be using, there's like an FPGA to HPS bridge, and maybe that will need configuration on the Linux side. Like, I thought I'd probably just be able to read and write the memory from U-boot, and I think that's the case if I do, like, direct memory access from the FPGA. But my plan is to use the bridge, which I think the bridge is really just some convenient libraries that make it a lot easier to read and write memory, where I think you just get, like, an address and values, and you can just clock it out and write it. So there might need to be some setup on the Linux side. I'm not 100% sure. I don't know. I'm like really torn. I'm really scared to figure out like how difficult this is going to be to set up. So let's see if we can drop into a shell here. Because we know this is going to panic because it's trying to load some like drivers that are FPGA related. So let's first see, how do we persist this? So if I do echo boot args, that doesn't persist, so let's try and do this. Echo boot args, help save env. Is this gonna just save all of them? Okay, so if I now do a reset, let's just do a hard reset. Echo boot args. Fuck yeah. Okay. And then if we dump the environment variables, print. I love that tab completion works in U-boot and like like scrolling through history also works. I hated for a while where like they ran a really nerfed shell in kind of all bootloaders and like EFI, like UFI shells. But they're seeming to get better and better. Like, it's really not that hard to add support for, like, history and shit. So, man, I can't believe we have 260 viewers. I don't understand how I can not stream for so long and still have, like, people show up. That's fucking wild, chat. I appreciate you guys. Press a 2 in the chat if you're helping me feel like I'm loved and should stream. Okay, so aren't you streaming in your website? Not right now, just because that just takes a lot of setup to do. I had that set up on another workstation that I've decommissioned, and I need to get like a 2U or a 4U so I can rack mount that server. And then I can, basically I have those two workstations that I can turn into just servers for various things. Because I like host all my websites at home now. So all of my websites are just hosted right off of my desktop right now. Which means when I like reboot my computer, my website goes down. I'm not hosting name servers, so that doesn't really matter. So I don't like lose email, but just HTTP. So I'd like to have like one workstation that's pretty beefy that just runs all of my like internet-facing services, so I don't have to. It's a little easier to maintain them. But yeah, I got all my emails moved over to Proton from Google Apps. I was using Google Apps, but I just don't like big tech. I'd prefer to have my emails be encrypted and not mined for fucking data. So. Okay. Oh, there's an FDT file. Okay. So we could also do $FDT file, right? FDT file. And what about Zimage? Boot file or boot image? Which one do we want to use? Let's do boot file. Boot file. Is there any environment variable that has the root file? I don't think so. Nope. Okay. And then I'm just gonna make note of these environment variable values. Default ends, just so I don't lose these FDT adder. So boot file is image. FDT file. FDT file is this. Then we have the addresses. Hello? Kernel adder and FDT adder. Okay, this. And kernel adder A, B, C, D. Okay. FDT adder, kernel adder, FDT file, boot file, and then, yeah. Okay, and then we can set kernel args and persist them. Save, was it help save args? Save env? Yeah. So that lets us basically persist those. So those are already set up. And then this is boot into Linux. And so the question is, what script is run by default? Does anyone know? I missed the old setup. No ads. Yeah, I'll try and get that set back up. Really, like, I've been doing a lot of remodeling, so I had to move my desks a couple times, which means I took down, like, all of my streaming stuff and the, like, workstation I had set up that let me do my restreaming. Effectively, I need to set all those things back up again. I need to turn on my, Tibia alert thingy. You're gonna hear random noises. It just tells me, to attack a new monster. It just does some screen scraping to tell me when when I need to switch monsters. Just moved to Czechia. I get no ads on Twitch without paying them anything. Oh, that's nice. How's the dog doing? He's looking at me. He's sleeping. Hi, Bubble. Yeah, you're a good boy. Yeah, he's already having a nap today. We already went out and played. And we went out and got some coffee and we got him a pup cup. And he loved the pup cup. After giving him the pup cup, he was glued to me. I think he was either thanking me or wanted more. But that was really fun. FDT mod. Okay, so what here? Does anyone know what command runs by default? Is it like boot command? Is this what's going to like run? Like if I do, or is this run by something? There's also these boot scripts. I don't know if I have those. ls mmc 0. I don't see anything in here that could be a boot script. I'm pretty sure, however the boot scripting is being done, it's being run from environment variables. Use file? Can I use file? No, I don't have file. But yeah, my view is that, like, I know what all of these files are. None of these are commands, so my guess is they're actually getting the command from... I bet it's boot command. That would be my guess. Run FPGA config, HDMI init. So let's set that. Let's do set env boot command, and let's do echo boobs. Save env. Reset. Okay, so I don't know if that was the first thing that got execution. Like, in theory, there could be some other command that's invoking this command, but, I mean, that clearly ran that, and then we dropped into our shell. So, at least we don't have to worry about not dropping into our shell. So, there we go. So, what we should be able to do is set up... we should be able to just set these commands now. Set env boot command. Load MMC. Now, is this going to... How do I escape these so the dollars stay in? Does anyone know? Fuck. It's okay, chat. We can just reset. Save env. Or set env. The boot args, boot args. Echo apples, echo boobs. Echo boot args. Save env, reset. What? What? Is it boot arg? Boot command? Boot. Yeah, that one. Boot command. Unset boot args? Help set. Help set env. Set env. Boot args. Oh, I do want boot args actually. Save env. Now let's do set env boot command echo astiv echo boobs. Save env reset. Okay. And will this allow us to do $signs now? Set env. Can we use a holla holla get dollar? Echo echo boot command. That looks good. And this should actually echo that. Yes. That works. Okay. Look at that. We're doing some automation, chat. Okay, so this should be pretty easy. Set kernel args and boot default script commands and persist them. So we'll do set env boot command. You drive me crazy. This. Eh? Boot command. Okay. This should, in theory, boot Linux. The root partition should be set. It should make it to systemd, and it will like panic deeper in the boot. Let's go! Let's fucking go! Okay, so now it's just a matter of maybe flashing on like a more stripped down Linux that doesn't boot this deep or something, but like clearly we have a functioning Linux. Started VNC server. FPGA in it. I'm trying to see if there's anything in here that like really matters. Like, do we need to bring along any of these systemd things? Let's take a look at the boot log. Let's like see what it's actually doing. What board are you using? Like what keyboard? I'm using a Keychron 60%. I forget what keys. I'm still compiling Yocto project in Linux master kernel for Whistle 2. Compiling Yocto can take a really long time. Huh. What FPGA board? This is a D10 Nano. Yeah, see, it's almost a 10-year-old distro? Yeah. Which is what you'd expect, right? Okay, so let's see. Oh no, they're using slub. No, slub is good. We like slub. Slub's the new one. VGA. I'm trying to see like what all is getting initialized. NTFS driver, nice. Console. ST Micro, Mac. I think I will have Ethernet, right? Like Ethernet will work for me. Yep, here's the Altera HPS to FPGA bridge. And it's registering that. So those bridges are working. Region probed. Okay, so I think the kernel is setting up these bridges. I don't think that's a userland service that's happening post init. So in theory, just a custom init would work here. We could probably... how can we tell systemd to drop into a shell? Is there a way to do that? Otherwise, we can just override init with like bin bash, which I imagine there's a bin bash on it. So we could try that. Okay, let's reset it. Drop into our shell, and then let's just set init blindly to bin bash and just see what happens. Init is bin bash. Save and reset. Can I get this playlist? It's just YouTube continuing stuff. I don't even know if I can share this because it's just an auto-generated one. Yeah, I can share something. I don't know what this shares. I think this is just the song. I don't know. Maybe that is the playlist. Okay, yeah, there we go. We got a shell. Okay, so we have Etho. Let's see if we can get Etho working. Do we have IP? Yes. IP link. Oh, fuck. We got to give that an Ethernet address. Let's see. I think we can give it an Ethernet address. I'm pretty sure I saw documentation for that here. Let me go find it. So this guy, this Zangman guy, has written kind of this DE10 Nano write-up. It's really, really good. This is like how I like writing up tutorials and blogs and stuff. It's really well written. It seems to go into details that matter. 10 out of 10. Why am I not hearing my alerts? Are they in there? Oh, they are. They've been going off this whole time. I just can't hear him, I guess. Let me turn down. Let's see. I guess I just should turn these up. I guess this is just a really loud song. PA play. Arg. Okay. Systemd has an emergency shell. Interesting. Well, I'm okay with the bin bash. All right, so somewhere in here I saw something about a way to set the MAC address. I think I can search, right? MAC address. Building the universal bootloader. So I can set a MAC address. I'm pretty sure I can set it via U-boot. Where was it? Like building sock design, building this MAC address. I think this is baked in to okay, extra env settings, FDT file, kernel adder. ETH adder. Okay. So I think that's all I have to set. So let's reset it, drop into the shell and try this. Whoops. Whoopsie doodles. Are you serious? What the fuck's going on? Why is my clipboard being all clippy? Set env. This, save env. So let's see if that takes effect in Linux. I don't know why it would. It does. Fuck yeah. Fuck yeah. Okay, there we go. Now we have an Ethernet address, so that's good instead of zeros. IP link set etho up, IPA, IP link, IP adder add 192.168.1.69 24 etho. Dev etho. Oh, I guess I gotta tell it broadcast, don't I? Oh no, it has broadcast. Okay, that's what I thought. Ping 192.168.1.1. Okay, we have Ethernet. I don't know why Control C doesn't work. Hello? Okay, we'll just reset the whole system. Okay. All right, so we have Ethernet working. So yeah, we have, do we have ETH tool? Yeah. Etho, let's see, what do we have here? Cannot get device settings. Okay, no idea why. But we have Ethernet, we have UART, and that's good. So in theory, this should be enough that we can at least like stream stuff to Linux, save it to disk or RAM, and then offload that over SCP to my host computer so I could analyze kind of the recordings we make off the FPGA. So all we have to do is get data from the FPGA into Linux. That's literally all we have to do. So let's make our own init. Okay. Do I have Vim? Yes. Do I have Nano? No. Okay. Vim. Let's just call it Folk init. Cannot write. Oh, I need to make it rewrite. Read write. There we go. Boot args, read write. Okay, let's reset this little bitch. Drop into the shell. And then let's make this work now. Save and reset. Okay. But this environment's really nice. I think U-boot puts the Mac adder into the device tree overlay. Interesting. I've never actually worked with device trees. Oh, whoopsie doodles. And then we'll do init is equal to bin bash for now. Okay. Reset. Drop. Struggling. Save and reset. Okay. Okay, so now let's make an init program. Touch ass. Hey! Okay, we can read and write files now. And vim folk init bin sh. At the end, we're gonna run bin bash, and then we'll do IP link set, IP link adder, IP adder add etho 192.168.1.69 / let me make sure that doesn't conflict with anything. DHCP leases. I think I lease from like 100. Show service DHCP. I lease from 100. Yeah, so 69 is fine. So add an Ethernet address and then launch bin bash. I think that should work for our init, right? 192.168.1.169 / 24. Reboot. Really? How do I reboot? Okay, sounds like we just hard reboot. That sounds like the fix. Okay, easy. And now we set this to bulk init. And now we should have networking out of the box. Can you do IP equals DHCP? Oh, yeah, I could. I've done that before, and I actually, and then dev etho. That's okay. We still get a shell. Oh, God. Dev etho. And I can't reboot. Sync. And this should just work. Numerical result. Okay. Oh. Bruh. Add that IP address. Okay, this time for sure. Luckily, these reboot cycles are real quick, which is nice. Hey! Okay, I don't have resolution. That's okay. 192.168.1.1. Network is unreachable. And then we gotta up it. Okay. Dude, how do I get rid of the fucking console printout spewing? I hate when it does this, man. It's so annoying. IP link set etho up. Echo name server 192.168.1.1 into etc resolve.conf. Let's do that. Sync. Reset. So now we'll have DNS. I gotta slightly turn down the music for me so I hear the notification sounds. I'm gonna have to turn up. There we go. Okay, now I can kind of hear the IPA. Okay, what is this bitching about? Is there no Etsy folder? Why can't I do that? Why can't I do this? What do you mean? Am I crazy? Hello? What? Ah, okay, it's a symlink. Okay. Can you boot Linux with log level equals 0? Maybe? Is there a kernel parameter set console to dev null? I think there is, but then I would like lose this console. I'm not 100% sure how the transition works. Yeah, does anyone know? Oh, look, our non-blocking pool is initialized. Look at that. Look at that. We can rand all day now. RMF etc resolve.conf. Sync. Is that all we needed to do? Okay, we have an Ethernet. We have an IP address. Our link is up. We have a resolve. Hey, we have DNS. We have DNS. We have networking. We've got everything, but we can't control C. We got to remember not to control C. Otherwise, we have to reboot the system. Luckily, the reboot's pretty good. This processor is nice, man. Okay, so we have literally everything. Okay, so let's cat proc IO mem. Mounts. Okay, we gotta get rid of this console spew. What the fuck can we do? Linux, get rid of console spew TTYS0. How do I do this? How do I get rid of it? Like how do I change it? Let's see. Dmessage N1. What does that do? Does that set the log level? So you're telling me if I open Vim right now, I'm not going to get interrupted by random shit? Sets it to emergency. What are the different levels? Shut the system up a bit by setting log level to... What are my log levels? Do we need to ask AI? Dmessage help has a list. Okay, just not in this. Oh, wait. Did I get something, or was that just because I resized the window? I think that's just because I resized the window. Ooh, do I have my really good script? Oh, I don't think so. Yeah, because like I don't have colors here, but if I do shell term, yeah, if I did set term X term 256 color, I don't think that takes effect there, but let's see if we can we're gonna make this such a good init. Aw. Damn. I guess. Okay. That's progress. Normally, Are any bash RCs I can run? Man, none of these are set in the colors? Yeah, I know I can set the alias to color always, but I like having it properly detect it because that means like other tools will also properly detect it. LS colors? Yeah, that's only for LS. Posted levels in stream chat, thank you. I don't know where I put stream chat. Thank you. Uh-oh. 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 Did I just freeze? Did I panic? What happened? What happened? I'm not getting any responses. Okay, we'll reset it. Oh, it's freezing. Why is it freezing? Is that because X term? Is that it? Is that the only thing we changed? Oh no, chat. What have we done? Is it just the term? Setting that term an issue for Vim? Term equals Linux, Vim, Vulk in it? Yeah, okay. Okay. I can't use arrow keys. I gotta use HJKL. How the fuck you do that? H. I can use delete key. That's good. Okay. Let's see if we can Vim again. Oh yeah, does BusyBox not have colors? Okay, BusyBox does have colors. LS colors. Colors? Color? Colors? I don't know if that works on BusyBox. Ha, clicking. Spew shit, nice. I want LS to look pretty. Yeah, delete the swap file. Okay. Why can't I use fucking arrow keys anymore? I was able to use them before. Yeah, why can't I fucking use arrow keys? Is that the host? It's gonna be hard without arrow keys, chat. We got a HJKL. This is gonna take twice as long. What else do we have to add to this? Alias. LS is... do we use ticks? Or no ticks? Do I just do this? Do I... a space equals no space? Golden kappa, no space? Anyone have a golden kappa today? It's on you for using Vim with arrow keys? Okay. Okay, fine. Fuck you. I'm wrong. Needs to be quoted. Okay. Oh god. This is so hard. Oh no! I hit an arrow key. So we gotta do this, and then we gotta H J K. Okay, H. Okay, then we hit I, and then we hit single quote, and then we hit escape, and then we hit hold L, and then we hit I, and then how do I insert after? How do I move now? How do I move? You can't use HJKL to put. You can't. You can't. It's over. It's over. It's fucking done. You can't use A. It's over. It's over. It's fucking cooked, man. Man, it's yeah. Okay. Sync. Reset. How do you like our init? I think this is way better than System D. Like, look at this. Look at this. Bam! Fuck! Sorry, S'mores. Is that not how you alias? Do we need a space? Okay. Okay, dude. It's the wrong shell? Alias isn't the parent? How do I export the alias? Help alias. Add a bash profile? Bruh, I don't want a bash profile. I like how just LS is Prince High. Oh, that's so good. That's so good. Profile. Java home? There's fucking Java on this? Look at this. Look at this. You go A. You do capital A to go to the end of the line in insert mode. That's how you use Vim. And then we do alias ls equals ls color auto. And then you do Vim the folk in it. And then you use J goes down, and then you delete it, and then you sync. You always gotta sync twice, and then you reboot. And now we're gonna have colorful LS. You do O, press O. You can't use O. Well, okay, this doesn't work either. Root doesn't use profile by default, right? But it'll run a login. Look at this, 300 people here and you don't even know how to fucking use Linux. It's pretty embarrassing. If I hit O, yeah, that, I like O, login. Okay. This time for sure. Oh my god. Dude, let's do the god damn it. Echo. What's the name of what's our host name gonna be, chat? Pick a host name. It's alright, dude. After using Linux for 3 years, I can safely say I can exit Vim. BBBB. Footlicker, Scaly, Bear, Fritz.box. S'mores. None of these are good yet. Ganja? That's illegal. Illegal. FPGA. My God, you guys suck at these. No wonder you guys went into development instead of anything in the arts. I think we're just going to call it HJKL. Let's see a host name. Okay, let's think. God damn it, it didn't pick it up. There's no way I can use host name, right? Vim, hostname F, Etsy hostname. What does that do? Okay, let's just run that too. Maybe that also helps. Maybe that does something. It's just, you ready for? Oh fuck. You ready for this, chat? I'm gonna go up, and then I'm gonna do this. Look at that. Fuck yeah, I'm so smart. What if none is not a host name? Is this gonna work? Probably not. Oh my God. Look at that. Look at that. Look at that. We got colors. Dude, we literally have everything. We don't have NTP though. We don't have the time. Because I think it's system D, so it probably uses like time date control, which is not gonna work without system D. Okay, what else? No D-bus, yeah. Okay, let's get proc IO mem. Mount T proc FS proc FS proc. Oh, it's just proc. Oh, let's go. Let's add this in here. Man, this init system's pretty good. Look at this. Now we're gonna have proc FS. Best init system. Isn't this nice? It's way faster than system D. IO mem. Okay, so here's all the things. So we have Ethernet. Hey, no looking at our addresses. Okay? Gotta keep these private. We got the FPGA manager. Okay, why can't I like click and select on shit? How do I leave Pico.com? This is like a AXX kind of thing. AC control. How do I exit Pico.com? Okay, maybe this isn't a deep seat question. This is more like a 5-4 question. Press and hold the escape key. Yeah, no, that's not what. Jesus, that's not how you exit it. It's not A/. It's not that. AX while holding. Yeah. Okay. Do I have arrow key? I have arrow keys here. Dude, I don't know why I can't arrow key anymore. Why can't I arrow key in Vim? I was able to arrow key in Vim before. What did we do? What did we do to break it? I usually do Pico.com. Honestly, it seems easier to just manage your own init than using any out-of-the-box init system. Yeah, it's pretty accurate. Do we have a link to the playlist? No, it's just autoplay. It's just literally autoplay. Oh, now we get some skillet. Okay. Cat proc IOM. Sock USB. So we have one of these banks is good, I think. What I want to get access to like the C mappings. Do I have GCC? Yes, I do. Do I have Java? No. Good. Do I have Python? Damn it. Oh, it's Python 2.7. Oh, hello. We got Python 2.7. Oh, we also have Python 3. Does your terminal you're running Pico Common need a reset? Okay. How do we get rid of this job control message? How do we run bash without job control? There's gotta be a way, right? There's no way, man. Set SID? I don't have that. Alright, chat. I think we're just gonna have to make do with this. Okay. System RAM. So we need a C1000 range. Alright, there's a way to do this. GPIO controller at FF709. Do we have those? Yep. So we have like some of the GPIO controllers. So like we have a decent amount of stuff mapped. HPS. I think there's like C1000, but I think I might have to set some args to do it. Let's see if we can find that here. Writing the components. Mem. Let's trigger it. Let's trigger the SD-RAM. Okay. Part 3. Avalon MM Part 3. Allocate SD-RAM memory. We want to have some dedicated memory available to our FPGA. We have to inform the Linux kernel to not touch it. We have to add a kernel boot parameter to xlinux.conf, which is on the fat partition of the SD card. Add a boot parameter of mem equals 512 meg. So that's going to restrict the Linux kernel to only using the first 512 megs of RAM. Set the HPS registers to enable SD-RAM access. Struggled with this for a couple weeks. Found this article. We'll need serial access for U-boot. Copy the design partition, mount it. Copy that. Yep. Reboot. Break it. In the U-boot console, first set FPGA to SD-RAM peripheral to reset by writing 0 into the FPGA port reset register. This is at address blah. So this is gonna set FFC25. Do I have that mapped in here? FFC FFC. So I don't have that here, I guess. But I can do that through U-boot. Now we load that. The FPGA design has configuration bits on the bridge that get enabled when we flash it. Needs to be done when the SDRAM bridge is in reset mode and when it's not being used by the HPS. Okay, so that's loading the RBF, which is programming the FPGA. Now we write a 1 to apply config. And then reset, and then boot. Okay. We'll hang when the FPGA tries to access the RAM. Create a boot script. Write the desired value to that, 512 meg. Let's trigger the SDRAM reader by writing to the starting address of the HPS FPGA bridge, which is at C. Trigger the SDRAM reader. Write the desired value. Okay. Yeah, Linux is running in the hips. So we want to... How are we... we just need to write RAM. Let's see if we can do that with the, let's see if we can do this with the Avalon MM, which is what we want to use. So let's go back. Avalon MM. I'm pretty sure this lets us just read and write memory. This is a follow-up to that primer on Avalon MM. Okay, primer. Here I will walk you through a high-level summary of the Avalon memory map. Detailed reference, that's the actual Intel spec. Introduction to buses. Yeah, basically we're sitting on AXI bus for the hard processor. Avalon memory map. The Avalon memory map is quite simple. Every port on every module of the FPGA fabric can be made available to the HIPS via a virtual memory location. That means if we want to pass some data to the FPGA from our HIPS, all we have to do is write a memory location in the HIPS, and the FPGA will just pick it up. But how do we interface with the Avalon memory map? By using AXI bridge. If you recall, when we're editing the HIPS in the platform designer, we enabled the HPS to FPGA interfaces and the AXI bridges section. Part of the ARM core, this bridge is what enables us to interface the HIPS with the FPGA. Okay. ARM cores can only use AXI, and Avalon kind of hides it. So there's 3 things available. FPGA to HIPS, HIPS to FPGA. It makes available 960 megs of memory space for data transfer, high speed, and should be used for low latency data transfer. So that's what we want. We're going to be using the heavyweight one, which is major communication channel, a high performance interface with configurable data bits, allowing the HPS, we want this one, the FPGA fabric to have full visibility into the HPS address space. That's what we want. FPGA slaves. Okay, so the FPGA uses address space, cool, but Linux does not. Linux just gets memory, I think, at 0. Yeah, I think just system RAM. How big is this? It's not everything, but it's close. Okay, so We want to be a FPGA slave, and then I think we just like add an Avalon thing, and we might just be able to write over memory. Right? So in theory, we just need to add one of these bridges to our project. Hopefully we can just add the Avalon memory map. I don't know if we need to add the hard processor system and then like enable these things. Probably, because we probably have to give it a clock or something. I'm not 100% sure how we connect up to this. But my view is we just can write memory directly. Like, my view is this is just going to give us memory access to RAM. And it's going to handle synchronization for us and stuff. So let's see what we can do. Our IP catalog, we have memory controllers, hard processor, I2C to MM master bridge. Not that. That's SPI. JTAG to Avalon. Where would I be? Where would I be? SDRAM communication. Read data. We need... Because, yeah, this looks easy as shit. Burst read. Okay, so we kind of have all these. So this is the Avalon interface spec. HPS technical reference manual. This is also probably really nice to have. HPS address spaces. FPGA to SDRAM. Okay. Common address ranges. HPS space. Yeah, this is all the peripherals. On-chip RAM. Okay. Technical spec, bursting. How do I set this up? If you haven't done it already, doing this. Okay, SDRAM controller. Yep, there's some magic interfaces here. Better block diagram. Be writing our own custom master component, which will perform all of the necessary steps to read from and write to the 1 gig of SDRAM available on the DE10 Nano. Okay. Avalon is fairly comprehensive. It increases if you're writing a host, master component versus a slave. Agent just has to respond to whatever responses are being made by host. The host, on the other hand, has to not only respond to the agent's responses, but also manage the bus. This is a host-provided HPS FPGA bridge for the SDRAM controller since there is no host. Oh, I see. So this is directly using the SDRAM, right? And we don't need that. So I think just the hardware adder project. So I don't know if we have to use the GHRD, but this has the SOC system. ARM processor components. So let's just straight up follow the tutorial. Let's just go through the tutorial first. So we have the GHRD here. This is the basically what they start with here. And we've done the IP upgrade. I've already done that. Upgrade the IP components. Then we're going to go into Platform Designer. So open up Platform Designer. This used to be QSys. So Tools. Platform Designer. And then we're going to load socksystem.qsys. This is going to add a bunch of shit to our system. Okay, so here we have HPS. We have kind of a bunch of things set up here. Should automatically upgrade your IP cores and then trim the system. Okay, so we're going to remove things we don't need. So first time you look at it, it looks daunting. We're going to remove things we don't need. We'll remove everything except for clock 0 and HPS 0. So go ahead and delete everything that isn't clock 0 and HPS 0. So I guess sysid, and then bridge. Okay, a lot of these things seem pretty important. Okay, so now we have HPS 0. It should look like this. Oh, this is this in theory showing me this block diagram? Oh, right click and edit. Okay. So there's still a shit ton of features. I like that we're kind of trimming it down. So then edit this. Okay, so now this is our hard processor system. Can I not? Okay. So then, there's still a bunch of features in here. Let's go to edit. So disable the trace macro cell. So get rid of that. Okay. Under AXI bridges, FPGA to HPS interface to unused. Or wait. Oh, are we doing HPS to FPGA? FPGA. Okay, so HPS to FPGA. We'll be using this interface. Should be the only thing enabled. Okay. Under AXI bridges, set that to unused. To this. Okay, so this is the FPGA SDRAM interface. Okay. Remove this. Okay. Thought we wanted that. Under resets, remove everything. Under interrupts, remove everything. Oh, I see. Okay, so we have like a much, much simpler diagram now. Under peripheral pins, set every pin to unused. 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 Okay, I think we did that. Maybe this one, unused. Unused, unused. Dude, I think we're crushing it right now. It should look similar to this. So we got under the mux table, disable every GPIO button that is currently enabled. Oh god. Oh god. Oh no, that's a lot of work. Okay, let's just see what we get. Memory conduit. HPS IO. I guess we have IO because we're using MMIO. Warm reset. Okay. Save it with Control S. Okay, let's see if we can bang these out. I don't know how hard it is to modify these. You missed a reset signal? Where? This? You're right. Okay. Now the IO, I imagine the IO is there because there's GPIOs. So pins are all unused NA, and then GPIOs. I want to do what? What do I want to do? Disable every button that is currently enabled. Oh, so like 9 and 0 and 35 and 40 and 53, 54, and 61. Okay, so those GPIOs are like, what, no longer muxed, I guess? So everything's unpressed, so finish. Hey, we don't have an IO conduit. Okay, so now we have memory, H2F reset, AXI clock, and master. Okay, that matches what they have. And then the clock in, reset, clock, reset. Okay, so see, what I really like about this tutorial is this tutorial does stuff kind of the same way I do, which is to kind of remove out all of these things that we don't need. Okay, Control S, and then generate HDL. Or do I hit finish? Oh, generate HDL down here. Okay. Generate with the default option. So this is going to go to SOC system in Verilog. Generate. Okay. So this is going to be generating, I guess, this system configuration. Nice. Okay, completed. Close. And then click finish. Close that. Okay, that closed the platform designer. You've created an IP. To add it to your project, you must manually add the QIP. And that is in SOC system. I think it might already be in there. Blank synthesis. Yeah, SOC system. We already have that included, so I think that should be okay. It's going to give you a module for the hips, yeah. And I think that was already included in this project. So now let's trim down the code. Now that we've removed many features from the design, there's a lot of Verilog code that we don't need anymore. Let's remove it. So they're in hierarchy. Double-click the base design in the hierarchy view to open the Verilog file. So this. So this is basically the entry point, I forget what it's called. What is this called? The like top level module or something. So this is what it generated. So our clocks, our HDMI pins, our HPS pins, the keys, switches, the LEDs. Okay. In Project Navigator, switch to Files and open the SOC base design called SOC System.v. Okay. In the file D10 nano GHRD, if you scroll down a bit, there's an instance of SOC System which has a bunch of ports that aren't needed anymore. Yes, these. There's also some IP for debouncing, which we're not using anymore. We need to remove everything that's not in use. You can do this yourself, or you can copy and paste this. Thank you. Okay. Compile the design. Save it, and then compile it. If this should build. So we're going to compile this. This is now making the system that we can then send over to the FPGA. Create a backup of the project. Yep, I'm tracking this project in Git, so we'll be able to check this in as like bare bones. So in theory, this is hopefully like one of the simplest setups. I don't think we need debounce and these files, so we might be able to remove these files. I'm pretty sure. Did it tell us to? There's also some IP which are not needed. Yeah, I'm pretty sure we can get rid of like everything here except for SOC system is what's made by us. Do we need the HPS reset? I think so. I think that was part of the platform designer. I think that had some reset shit. HPS to FPGA reset. Okay. I'm not sure. Okay. So this should build. But yeah, this is a counter, LED level. This is basically just flipping the LEDs, right? Or we have a counter here. Compile the design, and then if it compiles without errors, you can go back to the terminal, make a backup, and then we're going to the simple adder. Here we're going to make a simple adder module. While an adder is quite simple, there's one important note. We're creating a regular adder in Verilog, which would be just how you would have designed it if you're going to use it in a simple FPGA and not a SOC. This demonstrates how you can take an existing design that works in FPGA and reuse it in a SOC. That is really cool. So we're going to make an adder that has input, AB, outputs a sum, and yep, that's it. And then this completes the adder. Okay, so yeah, we'll be doing that. File selection dialog is very Java. Yeah, it's all very swingy. Oh, thank you for the 20 bits. I didn't realize that effect used bits. It doesn't like show up with 20 bits. I have to look at the activity feed. I guess I'm supposed to be a good enough streamer where I just like know that, I guess, question mark. Okay, it built, everything built. So I should be able to, I am in Linux, my Linux is working. I should be able to go into my programmer and I should be able to flash the FPGA. Yes. And now I have a flashing LED and Linux is still working just fine, right? So I was able to flash and change the FPGA software and everything just worked. So that's really neat. I think this tutorial is expecting that you're going to like put the programming file on the SD card and then use Linux to actually program it. But I'm not doing that here. I am directly programming it over JTAG, which is what I want. It makes the dev process a lot tighter, so that's where things might differ from this tutorial. So I'm a little worried about that, but I'm hoping we can make all of that just work seamlessly, because I really don't want to have to, like, fuck around with files. Okay. Yeah, it's really cool. Like, right now, I really like that we can write the FPGA and change stuff out live. Is that a softcore CPU? No, it is not. It is a hard CPU. Okay, so in theory, I should be able to delete debounce. I imagine I can get rid of the edge detector And maybe the interrupt capturer? Can I get rid of all those? Did I fuck things? Because now I removed them from the project. And hopefully this still builds, right? Because I don't think it was using those. I don't know if it's using this HPS reset. Well, really, unless my top level module is using it, it's not being used. Is that correct? Right? Like, I should be able to remove this HPS reset. Let's stop this. Let's just delete this too. Because we just need the system sock. The SDC file defines kind of the clocks for the simulator. Or like timing validation. I'm pretty sure just this will be fine, right? I don't know why this Verilog file doesn't show up in the project navigator. Like, it's in here. I don't know why this Verilog file is not in the project. I'm just going to add it to the project. I don't think it has any effect. Let's stop it again and just restart the build. Okay, this should build. We have the system that we generated, the sock system, and our top-level Verilog, which literally just defines the sock. And that's it. FPGA resets, clock 50. Okay. We'll see what happens. We'll see what happens. I'm spooked. Chat, can we get over 300 viewers? Holy dick. We need like 10 more viewers. Okay. Just waiting for this to build. But yeah, then we're going to make this simple adder. Save it as a full, save it as IP. Tricia, 300 people are watching a FPGA stream? Yeah. I don't know. I mean, I'm not a FPGA person, but I think I will be with this sock. I mean, I don't see any project that I'd ever develop that, like, this isn't good enough for. Like, an 800 megahertz ARM processor. I think it's dual core. Yeah. Dual core, 800 megahertz ARM v7, like, full-featured hard processor with float and vector, I think. Maybe no float. I think it's hard float. And then an FPGA with, like, what? How many? Like, 100,000 logic elements? Like, this is a pretty potent board for $200 and a nice case that I can just build I can just mill out, like, a aluminum box or a, or like a nylon or just some plastic box, trivially. Like, I don't know. This is really good. I could hook up so many sensors to this, have it automate and control stuff. And in my opinion, $200, yeah, like, you can go cheaper than that, but I'd rather have, like, the FPGA and the real-time abilities of the FPGA and then rely on a proper, fully featured Linux to, like, just kind of stream the data over memory and then process it where latency doesn't matter as much on the Linux side. Most ARM A-series are hard float. Yeah, I'd expect they are. 302 viewers, let's go. Yeah, that's everything. It really does. It's a really good dev board. Okay, everything built. So, yeah, I mean, what are we using? We're using 253 registers. Logic utilization, 20 ALMs over of 41,000. So we're basically using, like, nothing in the FPGA. This is just all wired up. That's really all this is this has, like, wired up the HPS communication mechanisms. Okay. So now what we're going to do is we're going to make a new file. We're going to make a new Verilog HDL file. It's going to be this simple adder. And then we're going to save this in IP simple adder. What's SV? System Verilog? Simple adder.sv. Add file to current project. Okay, so now we have system adder, simple adder.sv. Oh, fuck, wrong folder. Whoopee. New system Verilog HDL file, paste, save. They put it in a folder. Can I delete this file? Fuck yeah. Simple adder.sv. So IP simple adder.sv. Just want to make sure all the paths match so we can maybe copy paste some commands if we need to. Okay. Save it. And I should just be able to build it, right? Maybe not yet. Okay, primer on Avalon MM. Here I'll walk you through a high-level summary of the Avalon memory map. I would recommend you go through the detailed reference, which this is the actual specification, which we have open here. Buses are fundamental to all digital electronic systems. They ensure that data is communicated from one module to another reliably. There are several popular bus interfaces available to use these days, and each of them have their pros and cons. Bus interfaces may also have different variations within them for specific functionalities. A few of the popular buses are the AXI bus interface, owned and developed by ARM. This is used wherever ARM architectures are used, whether they are hardcore HPS or softcore like NIOS. This is pretty common with Xilinx boards as well. Okay, so AXI is just like the standard memory bus or standard bus used on ARM systems. Avalon bus interface. This is owned by Altera/Intel. And is what we will use here as well. There are several variations of this bus. So streaming for like streaming data, burst, which is like read V, write V, I think, like where you can do like multiple memory operations kind of in like one transaction. But we'll be only concerning ourselves with the most basic form of memory map with as few signals as we can get away with. Fantastic. That's what we want to do. And a Wishbone bus, which is some open source thing with no licensing. So the Avalon memory map is quite simple. For every port on every module on the FPGA fabric can be made available to the HPS via a virtual memory location. This means that if we want to pass some data to the FPGA from our HIPS, all we have to do is write a memory location in the HIPS, and the FPGA will just pick it up. So in theory, I think we're defining this like input A and B and the output sum, and I think all we have to do is just like write to some magic memory location in the HIPS, and it will send that to this module and maybe trigger the module to run. So we'll see. But how do we interface with the Avalon memory map? Using an AXI bridge in the HIPS. If you recall, when we were editing the HIPS in the platform designer, we had enabled the HIPS to FPGA interface in the AXI bridges section. These bridges are part of the ARM core that is used in the HPS in the Cyclone 5. This bridge basically is what enables us to interface the HPS with the FPGA. Yep, so we had that 64-bit HPS to FPGA interface. You may wonder why we're using AXI bridges to interface with the Avalon bus and also how it works. ARM cores can only use AXI bridges because that's what ARM owns and licenses out. Platform Designer hides away the complexity of connecting it with the Avalon interfaces by automatically adding in an adapter that converts AXI to Avalon. So basically, we're going to be using some simplified interface using Avalon, and Avalon under the hood, like this IP that's been generated, will correctly interface with AXI. So the actual hard processor is using AXI. we will also be communicating with AXI, but we won't directly have to do AXI. We will be doing Avalon, which is just going to abstract away some of the complexity of that bus, because I imagine there's like way more synchronization primitives and probably cache awareness and interrupts and all sorts of shit. And I think Avalon is really just making it as easy as possible to interface with memory. However, we need not worry about it here since the magic is hidden away for us. So there are 3 bridges available in the HPS. The FPGA to HPS bridge. This enables communication from the FPGA to the HPS. We won't use this. The HPS to FPGA bridge. This is the heavyweight bridge that allows the HPS to communicate with the FPGA. It makes available 960 megs of memory space for data transfer. It is high speed and should be primarily used for low latency. And then there's the lightweight HPS to FPGA bridge. This should be used for control ports. So like read, get status, etc. Most of the examples you'll find online use the lightweight bridge. It has 2 megs of memory space and is slower than the heavyweight bridge. Main purpose is to take away the pressure from the heavyweight bridge for reads and writes that don't require low latency. Okay, so basically, I think lightweight HPS to FPGA bridge allows you to just like basically do like simple in and out, but HPS to FPGA, I'm pretty sure is basically just like shared memory. The details of the bridge is explained in the Cyclone 5 technical reference. That kind of goes into more. We can see that FPGA slaves, we get this 960 megs at C. And to write a module that interfaces the Avalon memory map, we should adhere to the standard protocol that is required for this. There are 2 kinds of protocols that you can make depending on the flow of information. Host, previously called master, and agent, previously called slave. In this project, we are going to write our own slave modules, which will work with a master module IP that manages them. There are several options for ports that we can use for our modules, but for slave modules, pretty much all of them are optional. Some of them are clock, reset, write data, read data, and address. There are many more that you can see in the specs, in the references at the bottom. There are also some constraints. Whenever you include write data, you also need to include write as well. I won't go into detail. Okay. Basic intro. Okay. So next is custom Avalon components. So here we walk through the steps to create a simple Avalon components that'll help us interface with our simple adder. So the goal of the components, we want a way to write and read data to our simple adder. So the adder has 3 ports, 2 inputs A and B, and 1 output, and it's a 64-bit adder. We'll create custom input and output components that enable us to read them. Avalon sounds like a vendor lock in hell, yeah. This is so basic. Surely there's something readily available. There is, and that is where the IP catalog comes in. If we go into the platform designer, there's a bunch of IP in there, and we can just drag and drop them in. Normally, that's what you would use because they're tried and tested. There's one module that's designed exactly for this. It's parallel IO and can be found as shown PIO. Okay. Many reasons we're not using this. So we're not going to use this because many online examples already demonstrate this. Parallel IO only goes up to 32 bits, and we take 64, and we're going to do it ourselves. Okay. Learn how to write these. We have 2 inputs to our adder and 1 output. We'll need 2 different kinds of components. One which will allow us to write, and one which will allow us to read. Note that when we say output from a custom component, we're referring to the direction of the port that is actually used in the component itself. So an output will be connected to the inputs of our adder and vice versa. Okay. Yeah, it's really like, what perspective are you? Are you from the HPS or from the FPGA perspective? Looking at our interface requirements for the Avalon memory map, we will require the following ports. We'll need clock, reset, write, which indicates if we're writing or not, write data, which is what's being passed, and PIO out, which connects to one of the inputs of the adder. With this, I came up with this module. So PIO 64. If reset. Okay. If right, save this to the working directory. Okay, let's just give this a go. How do we make the Avalon memory map? Because we like got rid of the memory map, I think, or something. Okay, new system Verilog HDL file. We're gonna save this into IP PIO 64. And then we're gonna save this as PIO 64 out.sv. Same thing for the input. New. This is also in PIO 64. This is this. Okay. So back in the platform designer, create a new component. Add file. Click on analyze. Okay. Okay, I'm really confused how this is all gonna connect up. I thought this is using like memory read and write commands, but maybe not. Okay, so let's go into the platform designer. Let's go into, so I guess when we open the platform designer, we want to be in SOC system, right? Pretty sure. Yeah. Okay, new components. So we're gonna call this PIO 64 out, parallel IO 64-bit output. Go to the Files tab, add IP PIO out, and then analyze. Okay. Click on signals and interfaces. Okay, so S0 must have an associated reset, and the slave must have an associated. How does this know it's Avalon? Right, like, what did we put in the file that makes it know that it's Avalon? Like, how does. Or is this just here by default? So rename Avalon Slave 0 to PIO. It's this. Change the type to conduit. Associated reset to reset. Click on the signal, read data. Signal type export. How the fuck are you able to figure this out? This is nuts. Okay, so we're exporting a 64-bit PIO out signal. Okay. Click on S0. Change the associated reset to reset. Now we should have AVS S0 write and write data here. Save the component with Control S and hit finish. Holy shit. Where did it go? Where'd it go? Isn't Is it? Oh, it's here? Create a new component for the input as well. Okay. All right. PIO 64 in. I like don't know what I'm doing right now. I have no idea what's happening. Files. Oops. Didn't mean to do that. Where the fuck I just did there. Add IP PIO. This is the input. Analyze. Okay, so now that like found inputs and outputs, and then we're assigning these. We don't have to do anything here? Repeat the same steps as we did with out, but with in. Okay, still don't know what we're doing, so we got to do all these things. Oh, God. We did that. We analyzed it. We rename this to in. Set the type to conduit. Associated reset to reset. There you go. PIO in. This is export. S0 associated reset with reset. Okay, so we got rid of all the warnings, so that's good. So that I imagine that's like what we did. Okay, and then Control S, and then hit finish. I still don't know what we're doing. Okay, so we need 2 outputs, and we need 1 input. Okay. And then we need an MM pipeline bridge. Okay. So are we just dragging and dropping these bitches in here? Put everything together. Okay, there's nothing in here yet. Good. Double click on the pipeline bridge. Okay. Which is in memory mapped. Basic functions. Bridges. Memory mapped. MM pipeline bridge. Double click. Okay. I think this is gonna give us something that like lets us like talk to Avalon or something, and then we're gonna like hook this in. This is telling Quartus how to interpret your module so the tool can hook it up on the bus. Yeah, and now we're like making the bus, and then we're gonna like hook up the modules to use the like this clock and reset and bus and stuff. Okay, we're setting the data width to 64. That's good, I think. Symbol width is 8 bits or 1 byte. Okay. Okay, and we're just leaving the address width and its symbols. Okay. Okay, we click finish. Okay, this did a bunch of stuff, and we got some errors. That's good, maybe. Okay. Complete the bridge configuration by wiring the signals as shown. Okay, okay. Oh, shit. Unconnected. Clock needs clock 0. Okay, and then reset needs to go to something. And then the memory map slave, this needs to go to what? Base? End? How do we do that? How do we do this? We set the clock, that's good. That's good. Do we have to like click these things? Are these things we do? Do we click like this? Okay, the HPS AXI master is going into the slave. Okay, I clicked that. That did stuff. Okay. All clock signals should be connected to the same clock. All reset signals should be clock 0. A reset. Do I just click this? Okay. So clock reset goes into the reset for the bridge. I see. So we care about this side. Okay. And then that's forked, and then that's connected. Do I have to click on this? Is that important? Or do I want that? Or do I not want this? They don't have this in this photo. Reset signals are all clock reset. This UI is crazy. Yeah, this UI is fucking terrible. I'm sorry. AXI master should connect to the slave. That will be connected to the other slaves in our designs. So M0. Okay. Clicking on the thing, clicking. Okay, I set assignment. So we got a warning. HPS. So we want this reset connected, right? No. No, that's connected here, which is good. I think we did the connection we want there. Right, so now we've set up the MM bridge. So basically this MM bridge has been connected to the HPS. And then this master is on that at 0 to 3FF. Okay, so that message is good. That's good. So now we want to add export our conduit. So they're available to be wired to the simple adder. Okay, so we're going to export those as adder A and adder B. So we need to add 2 PIO outputs, right? Okay, so we add 1. Add 2, and then we have to wire all these up. Oh, fuck me. I click on this, and I click on this, so the clocks are wired up. Right? Okay. And we wire up the resets to clock reset. And then the M's get connected. But the outs don't get connected. Okay. And then we're going to export these as adder A and adder B. Oh my god, this is so weird. Okay, so though we connected the clocks, we connected the resets, and then we're exporting... what about this? What about this conduit? Do we need to click something here on S0? That needs to get connected. I think the S's need to get connected. So I think the only thing not connected is... Are these? Wait. Oh, wait. Wait. PIO. Wait, the conduit is exported as adder A. Mine is in a slightly different order. That's what threw me off. Okay. So basically, I think what we've done... I think what we've done is we've basically said that these will be connected... These are exported... And then we will be connecting these to our Verilog code. but the slave and the reset and the clocks are connected to the clocks and the resets and the other buses, and we don't have to worry about connecting those. So effectively, the only things that are left hanging are these PIOs that we've exported, and now we're going to be able to connect those into our actual system, into our Verilog. Okay, what's going on? What's these? M0 PIO overlaps. Uh-oh. Oh, because we have to assign these numbers, 0 and 8. Ah, we're assigning addresses. Okay. Start and end. Where the fuck did that just go? Okay, so now we're actually adding the addresses. So we're basically saying that there is 64 bits of memory that is being made accessible at address 0, and then this is at address 8, and it goes to 7, this goes to F. So this is determining like what will actually read and write from Linux. And then that overlaps with this. Do I have to like change the address of this slave, or did I connect this slave wrong? This S0. I think this is not supposed to be connected there. I think. AXI master from the HPS goes into the slave of the bridge. And then this hosts a master, and then we have slaves on there. Oh my god, I think it's starting to make sense. Okay, so we have the hard processor. This has a clock that clocks everything. So everything is clocked off the same clock, which I think is correct. Then the AXI master from the physical processor talks to a slave of this Avalon bridge. That bridge then hosts a master to multiple slaves. This master bridge maps in 512 bytes of address space, which we then separate into separate slaves, one which maps in 64 bits at 0 and one which is 64 bits at 8. And then they're all clocked and reset by the same thing. The output of these two outputs are not connected to anything because we will be connecting those to our Verilog. Don't worry about the error message. We'll deal with it soon. Okay, then we're going to add the input. Let's see if we can try and figure out the input ourselves. So the input, we're going to connect the clock and the reset. Am I doing the reset correctly? I think so. Because reset is connected through to here. I don't think we bring that out to everything. And then S0, so we're adding another slave. This is now conflicting. We're going to need to give a new address. Let's just say 10 hex. Now there's no conflict there. The reset the clock, and then the slave is connected on that slave bus. And then we're going to export adder sum. Nice. Mapping the memory. Let's talk a little bit about memory addressing. We want our components to be accessible from code running in the HPS by writing or reading certain memory locations. This is done as follows. Memory location on the bus. We'll be using the heavyweight AXI HPS to FPGA bridge. From the Cyclone V, we know that the address for this begins at C. Not relevant to us yet, but putting it here for completeness. Strictly speaking, the components in our design will be addressable from this location onwards. Okay. So we are exposing... Okay. Also location of components. Every component is available at a specific offset from the bus memory location. This is shown in the base and end. We see that MMBridge 0 maps 0 to 3FF, 1024 bytes. This is an important point to remember. All the addressing is done in bytes. Remember, we have defined our input and output components as 8-byte components. We need to provide 8 bytes for each. The base and end addresses for the 3 components we added is exactly the same, which won't work. Each one needs to have its own non-overlapping address space. For this, we edit the values. I prefer to keep them contiguous, but they can be any address as long as it's within 3FF provided by the bridge. Auto adjust. One step I missed is to enable the option to automatically adjust the address width. If you click on MMBridge 0 and click edit, you'll see an option to specify the address width. It currently sits to 10, which is why the address for the pipeline bridge is 3FF. I see. We can enable an option to automatically determine the address width, which will automatically adjust it depending on how many components we have connected. Okay, so if we edit this, we set automatically, and then we don't have control of that. Now, it has minimized the space to probably the nearest power of 2 that fits all of the components that we have added to that bus. Okay. Note that the end addresses, nothing has changed there. Generate the HDL and finish. So hit Control S. And then generate HDL. Generate. Okay. Add the simple adder. Okay, so now the SOC system is going to just have some wires that just show up. Finish. No way. So if we go into... Yeah, there they are. Adder A export, adder B export, adder sum export. And yep, they're 64 bits. And those are now just part of our system. So now, in our base system, which is this, we can add... We're going to add some wires. 63 to 0. Adder A export. Okay. B. And sum. And then we're going to make an adder. Simple adder, my adder, adder A export. So we're wiring this up. Some adder sum export. Bam. And then we're going to hook this up to the system SOC. So we've defined the wires, we've connected them to our adder, and now we're connecting them to the system. Some exports. Okay. Let's add the necessary wires. There's one line in the file that is not needed anymore, which I hadn't removed earlier. If it complains during compilation, you can remove it as well, or you can copy-paste the entire code. Here's the complete source code. Okay. So it's basically what we just had. So now we have an adder that is connected up. And then we're just going to compile it. Okay, before we can start using any of the bridges, we have to enable them in the device tree. This is covered over here, so I won't be doing it again. In the DE10 Nano, check that the bridges are enabled with the following command. If they're disabled, then you get an error. I think they are enabled for us. Mount T sysfs sysfs sys. And let's add this to our Folk init, just so we have this. Okay. The last one is enabled. If they're disabled, okay. Which one is enabled? We can flash the design onto it. The blinking LED to indicate that it's ready, and then we can write software to interface with it. It's a very in-depth hello world. Yeah, it's really good. So really, so has this like reserved memory? Like, do you have to... Like, how would I have, like, 100 megs? If I wanted to share 100 megs... Also, like, how is this all buffered and connected up? Does it monitor the... Like, when do these values get updated and shit? Is it done building? Nope. So once it's done building... We then just have to touch at C. Yep, adder, the bridge span. It's just, we're just gonna open devmem. And then we're going to just write into this, right? Yeah, literally just like a volatile write. So, like, when does that get updated? It's all transparently handled by adding that to the hard processor. Yeah, like, when does this sum become available? Like, when I write to these two things, how does this know how to block long enough? Is it just a race? Like, how does it know when it's available? Is it actually doing synchronization where, like... It waits for all of the writes to occur, and then it waits for the result to be produced. FPGA on SOC or MMIO. Yeah, I mean, but like... So these writes are a volatile, so this will happen on one clock, this will happen on a later clock because it's a different write, and then this one will happen on a later clock because it's on a different read, and thus it's fine. Because it's impossible to, like, have these two write on the same clock and read on the same clock, and thus this is a discrete event from this, which is a discrete event from this, which basically guarantees that the FPGA has observed this value by the time you read it. But, like, if I made the FPGA operation take a really, really long time to propagate, then I'd expect I'd observe an old value here, right? Like, we're relying on the fact that the FPGA has updated the sum by the time that this next Avalon read operation through the mmap could complete. But in theory, the FPGA operation could take significantly longer. So really, Avalon is probably snooping like the memory access bus from the hard processor and is seeing reads and writes, and when those reads and writes happened, it's just like slurping them up and then latching them into like an FPGA register. Like, these values aren't actually stored in RAM. We are not actually interfacing with SD-RAM yet. This is all happening through memory mapped IO at C000, which is being snooped by like the bus. That transaction is getting redirected to that like bridge, the master bridge, which is then seeing that it's accessing adders 0 or 8 or 10, and then that's getting latched into probably some allocated space. We've probably actually allocated some memory bits on our end, and then it's latched in. That it just behaves like normal logic in the FPGA, and then it just goes out in kind of the same way that when we read it, it's just reading whatever like register it basically has allocated, but there's no RAM. There's no like SD-RAM communication here. It's all based on like the Avalon and AXI buses. It's not reading and writing SD-RAM. Yep. So basically we see a transaction we see a transaction on the bus. This then determines that it's for an address that we have declared, and it has like automatically allocated probably some SRAM cells to buffer those accesses in flight. But there's no RAM happening here. We haven't done like memory mapping. We've done MMIO. We haven't done DMA. Okay, that makes sense to me. Okay, so that built, and then I can then push this with the programmer. So this is going to flash it. So we've uploaded this to the FPGA, but I don't know if Linux is in the right state to interact with this yet. We might have to get this bus up and running. Right, because we have some of these other buses, but we don't have the CO bus. My view is if it's not an IO mem, then we don't have access to the CO bus. So I think we need to get that to show up like something. I think maybe these aren't supposed to be disabled. How do we print which ones are here? I imagine these were just in order. So we don't have these bridges, but we have bridge 3. Okay, let's see. Fuck yeah. So the bridges that we have, FPGA to SD-RAM is enabled. So the FPGA to SD-RAM is enabled. The HIPS to FPGA is, the lightweight one is not enabled, but we're not using that. The HIPS to FPGA is disabled, and FPGA to HIPS. And which one are we using? We're using HIPS to FPGA, I think is the one that we're using, right? If I'm not mistaken. Right? What are we using? Where am I? I'm lost. I'm lost. I'm lost. Help. 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 Okay. Yeah, we're using here. We're using HIPS to FPGA. Which is not enabled. So we need to enable that on the Linux side. Okay. So let's go and figure out how to do that. But yeah, I think that is all mapped in. But yeah, we're not actually doing SD-RAM, which we're going to need SD-RAM. You could also run some simple no standard Rust program instead of Linux. Use the adder and print to the UART. Yeah. Oh, yeah. Yeah. Yeah, I like doing the HPS stuff is so easy to me. Like writing Writing ARM operating systems in real time, fucking trivial. Like, I've done that so many times. Basically, the software side of this is fucking trivial. Like, I'm not worried about that. I've done that a billion times. Basically, as long as I have RAM and code execution, everything's easy. Configure the device tree. Before we can start, we have to enable them in the device tree. Okay, and I think I can do that in the bootloader. Let's see. Let's do a reboot. Oh, just hard reboot. Drop into the shell, and I think this had something about the FPGA interfaces. This is actually loading the FPGA. Let's see. I swore I saw things on, like, how to set this up. Just use the M* commands. You can do direct MMIO. Yeah. Like MD, like memory dump, memory display. But I need to load this bus first, right? This is gonna just crash. MD, help MD. -L, I'm imagining that's 64-bit. Byte, word, and long. So dump, I'm gonna dump at 10. In theory, this should be a readable location. Yep, and then that resets. Yeah, and that is because we haven't actually set up that space yet. So enable the FPGA bridges. This is for device tree. Where's the CO? Because the bridge that we care about is this one. And so reg. I thought it was at like COO. FPGA slaves. Yeah, we will actually be using that. Okay. So my view is we have to get that to show up. The device tree is just talking to Linux. I don't think we need that if we're doing it directly from U-boot. You should see that they're all enabled. Unless it is here. Is it here? And then Linux maps it? I'm so confused. Where's the C? Like, I think that's what's really strange to me, is I have no idea where that's coming from. Like, is it this? Is this where it actually is? HPS to FPGA bridge. Reset that clocks. Status disabled. Okay. Oh, this bridge. This probably isn't directly where it's mapped. You probably have to create. My guess is that it actually. Like, does Linux hook the reads and writes to COO, and then that gets translated through to this bridge? Like, do I need a driver, or can I just get this to show up? Yeah, so this is part 3. This. Trigger the SDRAM reader by writing to the starting address of this. Doesn't matter what we write. Yeah, because this is... This... Basically, I think the lightweight... Basically, we're using... This bridge allows us to, like... Does this let us, like, interrupt? This is a different program. But my view is that this is still using the I/O so that we can, like, get a signal. I think this is doing something so that it like, notifies us when something happens. I haven't read through this stuff yet, but... Trigger components. A trigger for a host master. So Linux, how do I turn off dark mode in GitHub? How do I turn off dark mode? I can't believe there's not just like a easy slider. Okay. HPS FPGA bridge, a signal to trigger component. And then that will cause the Yeah, so basically they're going to use this like parallel input-output to allow us to cause a trigger by writing to that like COO, which is then going to trigger this to then cause the SDRAM reader to run. And then this is going to read the data and output it to the LED. Okay. So, yeah, basically, like from x86 terms, this is like an I/O port, right? An I/O port that's like sitting on the memory bus, like that's triggered by MMIO, or like your PCI base addresses where they're actually like sitting on the bus, and reads and writes are like packets that go out on the memory bus that it responds to, versus actually like using SDRAM. Okay. So what we want to do is we need to get that COO to show up. But is that making this? Like, do we have to enable this? How do we list the file? Can we cat? Is there a cat or like a dump file? How do I do that? Fat. Load binaries file. Like, how do I list a file? How do I cat a file? Anyone know? Anyone know how to cat a file? Because my view is like this bridge isn't enabled. by default, the device tree has all of the FPGA bridges disabled. You'd have to enable it. Oh, I see. Okay. Because, yeah, I can enable these. We can enable these, but in a child tree. Generate the tree. And then you make it. Enable the bridges. So do I need this bridge? Unless I want to basically, this is using it to do, like, interrupt signals. But, like, can't I just read the memory? Like, I would need to make a master bridge or something? Let's see what kind of options I have on stuff like this. Data width. 64. Address width. So I sit on that bus. How does it know that this is the fancy one? Because I have set up... Oh my god. Since I have set up HPS to FPGA interface, and this is the AXI master, if I do unused, I lose... These go away. Yes. Okay. So AXI master, AXI clock. So I've made those. Then I've connected that AXI master up to this bridge. The bridge, is the bridge where those registers are stored, or is it here? Block, symbol, parameters, signals, and interfaces. So this takes in a clock. We export 64 bits conduit. Like where save. Where's that register? Because this is a wire. I don't know system Verilog. Is logic like a wire? Is that a register? Like, are these the registers here? I'm just curious, like, who is responsible for, like, where are these 64 bits being allocated and stored? Is one question I have. Or is the bridge just making those for us? Because, yeah, like, is there not just an easy way that I can, like, drop in a way to read and write memory? Because this was bridges, memory mapped. pipeline bridge. Because streaming. Oh, Avalon I guess is Avalon memory mapped. So that's like you sit on the bus and you sniff addresses. Is it Avalon ST? Streaming. Clock crossing bridge. Because they do the SDRAM thing. Anyways, the bridge itself has MMIOs that enable it. I'm pretty sure I've seen ways to, like, write to enable the bridge. right? Like I'm pretty sure I saw a way to, for just mapping AXI over, you probably just need that AXI bridge. Yeah, this would put me on the AXI bus, right? And then I would have to do AXI myself, right? Because I want to be able to write to SDRAM, which they have another tutorial for it. But let's try and finish this tutorial first. Let's try and get this working. We need to get that bridge up and running. Let's, it might be time to like read the actual, let's see if COO, bridge. FPGA, bridge enable. Bridge enable. Bridge. Bridge. Help bridge. Bridge enable. Okay. Does that mean I can now write to memory? Like my view is that has enabled the bridges. Is that cool? And then let's do a, and then my view would be that now I have access to COOO, or do I want to use FF5 this? That's lightweight HPS to FPGA. Thoughts? Thoughts? Let's check this one first. I think MD quadword this dump 3. It's not quad, it's L. That hangs. Is it hanging because so enable bridges, and then let's try and dump only the last one. 10. This one should be readable. No. Fuck. Fuck. Bridge enable. Okay, let's see if maybe the C range is available. Oh, let's first make sure that, like, MDL... Okay, L is 32-bit. Do I need to do a 64-bit read? Is that the problem? Hey! Hey! Hey, wait. Bridge enable with this. Shut up, everyone. Shush, 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 shush. Shush, shush. Shush. Help. Is it MM? Nope. Memory help NM? Help. How do I write memory? MW? MW dash W. COO 1 2 3 4. And let's give a 69. We're writing a 69. And then we're gonna read the adder. Hey! And then let's do a 69 at 8. And then I guess let's do a 4. Let's write a 0. And then let's write at C, we'll write a 0. Oh, did that purge these? There we go. Okay, so it's just bridge enable. Yeah, we don't need to do all this dumbass shit. Okay, can we boot in this state, though? Hi, S'mores. How are you doing, Bobo? Hi. Yeah, we're streaming. Hi. How are you? Yeah? You having lunch? Yeah, I'm gonna have lunch too soon. Yeah, good boy. Yeah, who's a good boy? Okay, let's see if we can do bridge enable and just boot Linux. Hi, Bobo. Bridge enable. Hey, Dev Angels, how's it going? Saving. And then reset. Okay. So now we're booting into Linux. Oh, God. Okay. Cat proc iomem. So we don't have COO that is shown up here. Isn't there like a memory? There was like a BusyBox memory reader, right? That they were using for something. So now let's see if we can get it working. You have to add it to the device tree if you want Linux to see it. Is that true? Is that true? Devmem and use iomem relaxed. Does that mean Linux doesn't care if it doesn't issue like a bus error? Am I gonna get a bus error if I try and read that physmem? How the fuck did they read write memory? Where was it? Where was it? Let go. Mem. This. BusyBox dev mem. So you think this is like gonna give me a bus error? Write a... Oops. This address, write a 1. Applet not found. Go fuck yourself. Really? Getting scammed. You should be able to read it, but it won't show up in any of Linux's reports unless it's in the device tree. Yes, yeah. Fuck. The scam. Can you DD into devmem? It's kind of hard because you gotta do the skip. You gotta do skip, I think, or something, or seek or skip. Oh, seek. That's the hard part. Do I have XXD? Yes. I can't control C. We gotta reset the system. Is this terminus? Yes. Okay. DDIF is equal to dev mem. There's skip and there's seek. I seek. Input blocks. Can we just do BS as one? Can we do seek, or do we have to? We have to do skip. Skip. Please let me do hex. Count is 8. XXD. We want to read 10. Oh, fuck you. Fuck. I don't know if that's doing the seek that we think it's doing. BS is 1. IBS? No, just BS. Skip. Is skip not doing a seek? Can we add this IO range easily with the dollar $OXC? Yeah, I mean, and it doesn't matter though, unfortunately. Okay, so we do have a bridge set up. Fuck. I gotta go piss. I'm so hungry. Be right back. Hi, Bobo. Who's your good boy? Who's your good boy? Who's your good boy? Who's your good boy? Hi. Yeah, me streaming. We'll go play in a bit. We're gonna wrap this up and then we're gonna play. We'll go get some food. We'll go for a walk. We're gonna have so much fun today, S'mores. Yeah, you're a good boy. You're a good boy. You want a treat? Sit. Sit. Boy. Can you shake? Good boy. Can you lay down? Lay down. S'mores. Lay down. Hey, lay down. Lay down. S'mores. Lay down. Lay down. Lay down. Lay down. Lay down. No. Lay down. Good boy. Good boy, S'mores. Good boy. What a good boy. Okay. My guess is like, it's just time to write some code, right? Right? We just need code. Vim. Let's just go into home. Oh, there's no root. Oops. Vim read.c includes standardlib.h, include standardio.h, include sysmman.h, int main void return 0. Oops, can't use n, so we got to use o. Oh, look at that. Int fd is open dev mem. O read write. If fd is less than 0, couldn't open dev mem, return -1, close fd. Mmap void times map is equal to, or I guess we want to just seek, right? We should be able to mmap this, right? We should be able to do a null one page of is it prot first? Prot read prot write map shared map yeah, just map shared should be fine. Don't need really anything else here. Yeah, just map shared should be good. Then we'll do fd and then offset c 1 2 3 1 2 3 4. Okay. Fuck. Okay. If map is equal to map failed, pair could not map dev mem, turn -1, printf %p, new line map, gcc, read.c, fuck yeah, that's function, file control, control, cntl.h. Oh, and close, you want some unistd? Okay, we mapped it. Okay, chat, get your poggers ready. Everyone get your poggers ready. Do not place your poggers in the chat yet. Just get your poggers prepared, okay? Let's do a pogger preparation. IO space. Just prepare them. Just prepare them. We're not using them yet. We're not ready for them yet. We're not ready for them yet. Volatile, uint64t. A. uint64tb. Volatile. uint64t result. Do you need to make this pointer too? I always forget where fucking volatile actually applies. IO space pointer is equal to struct IO space star map. Pointer A is equal to 5. Pointer B is equal to 6. Printf %d plus %d. I wonder if I can read those. I don't know if I can read these. We're gonna fucking try it. I ain't scared. Pointer A, pointer B, pointer result. Son of a bitch. Student.hitch. Hmm. Hmm. Okay. What's going on here? Format string? Because these need to be LLs. We're on 32-bit. (11 + 11) is equal to 11. Okay. I think you just can't do readback on these. Fuck. For int I is equal to 0, for int a is equal to 0, a is less than 10, a plus plus b, b. A is equal to A, B. Now we're going to do an A and a B and a res. Okay, clearly that works. So just bus enable, bridge enable, load MMC. So bridge enable, load the kernel, load the fucking boot file, boot the fucking bitch, and then we're in. We're in. Look at that. Look at that, we're doing math. We're doing fucking math. God damn. Hot damn. Look at that. We could now mine some Bitcoin. Okay, let's get some output from our ADC. Right? Man, that's pretty good. That's pretty good, chat. Okay, so now we can just hack in our ADC, right? Let's add a file to our project. We're gonna add DRO-reader.verilog. Gonna hit apply. That's gonna take a long time apparently. And then we can go into the DRO reader, and then we're gonna make one of these. We're gonna make a MCP, which is so we're gonna get rid of the adder. Well, yeah, we can get rid of the adder. I ain't scared. Okay. Oh boy. Smart is playing with his new Sasquatch toy. Okay, we're gonna make an MCP. So can I open? Where's the trash project? Where'd I put the trash project? Save this project. Let's close this for now. Save. Save that. Sure. Okay. Sure. Generate those. I don't think we changed anything, but let's just bang these out. Okay, finish. Okay. Then we're gonna do trash. And we just need to add a PLL. How fast is this PLL running? I guess we can just like copy that PLL over here. ADCCSN. Oh, I redefined those pin names. Fuck. So I need to make a PLL. Okay, we're gonna copy these. Put them in my clipboard. Okay, everyone got your clipboard ready? Let's put them in our clipboards. Now we're gonna go over to the other project. And then hopefully it's still in our clipboard. Press 1 if you think it's going to still be in our clipboard. Press 2 if you think there's no way it's still in our clipboard. Oh, yeah, it's in our clipboard. Okay, then we need to define... we need to make a poll, and then we need to make our ADC pins. Our ADC pins. So let's go into our pin planner, which is this. And we should have our GPIOs. Where's our GPIOs? Hello? Hello? Are they not in here? Do we have to define? Do we have to define our GPIOs? I think we do. I think they got removed. Where are you? Where are you? I don't see them in here. Tisk. Okay. Okay. Let's go and just add them. Can I open another Quartus? I'm going to open another Quartus over here. Yeah, now I can open my trash project. And then let's go into our pin planner, our pin planner. Let's make a new node. ADC1 clock. I like when it just randomly fucking scrolls. That's great. Love it. Let's just keep adding these then. ADC1 CSN. Zoop. And zoop and doop. And then ADC1 doubt. Okay. Pin location. Let's do pin V12. And then we'll do a pin W12. And then a pin E8. This should be a 3.3 volt low voltage tittle. And Dev Angels, I saw your message about when I'm free. I'm going to get food immediately after this. I am starving. Sorry. Okay, that is... I think that's good. Okay, we've made the pins. Right? The pin planner. Now, this won't build now, I think, because those pins need to be defined here. Maybe not. I don't know. I have no idea. Okay, so then we should have our ADCs here. Fuck. Gotta really... Okay. It'd be really nice if Control-C worked. Jesus. Okay, so we've now defined these ADC pins. And then reset, we don't need that. We're not using reset, right? Oh, I am using a reset. Fuck. This is one of the switches. So let's go back into the pin planner. Which one's which? Trash. Okay, this one has it. Reset is AH17. Reset. Pin AH17. Oh, I see you. Yeah, chill. Chillax. Delete. AH17. Okay. Close that window, save this, close this window. Okay. Now all those should be hooked up. The only thing we don't have now is our pillow. Rare Gamoza stream, yeah. Oh my god, are we gonna cross fucking 300 viewers again? What the shit? How are there so many people? LEDs. Fucking damn it. Do we not have the LEDs pin planned either? We do. Thank God. Okay. We just have to define them. Output LEDs. Now we should be getting pretty close. This should just be bitching about the PLL. So we'll just make a pull. And we need a 3.4 megahertz pull. Okay. LED declared more than once. Okay. Yep. Yes, it was. Okay, let's make a pull. Do I want to use Platform Designer for the pull? Sure. 50 megahertz in. What did I say? 3.4 out? Don't care about locked output. Ref clock and reset. That looks good. Okay, and then the PLL 0, the clock input. What's this clock line? Clock 0. Is this the 50 megahertz clock? Yes. So I can just connect it here, right? If I do this, it's now getting... And then I can also connect the reset to that reset. And then the out clock is not connected, is the only thing, which is fine. So then what does this do? This... I should have a PLL with one output. Because before I manually defined the input, but I guess now I can like map it in with this. I didn't use the platform designer last time. So now for this system, I have an output from the pull. Daddy. Or do I have to make a pull? Is it this? Input wire ref clock, reset out clock. But haven't I like made that? Oh, I have to export it, right? Sorry, I'm not reading chat. Yeah, I think I gotta export it. Yeah, I've never done like the platform designery thing. I kind of like manually did this before. Yeah, I think if I just export it. Okay, this is starting to make a little bit more sense to me in terms of like actually what I'm doing. So we're just gonna call this hello. How do I rename this? Can I not rename it? Edit. Hello. There we go. Okay, now it works. PLL 3.34 megahertz. And then generate HDL, and then this will just show up on my platform as an output. And then I just make a wire and connect it up, and then I connect that into my program. Okay. Reload, yes. Yes. Okay, we can close this. Yes. Hey! Okay, PLL 34 megahertz clock. Oh, this is sick. So then I'm not defining the PLL like that. Instead, I'll make a wire for this. And then I hook it up to this. And now I have access to it. And then I can pass that into this. And now I'm clocking the ADC. And this should now build. And then I just need to 37. Okay. Fucking trailing commas. Is that what happened? Did I get trailing commaed? But I think this will build. And then I just need to export the output of the... Cannot resolve multiple constant drivers. 63. Because I'm driving it from this. Yeah, get the fuck out of here. Okay, so we hook up the system. And then the only code that's going to be running is going to be this MCP code, because we got rid of the adder. And I already deleted the adder. Okay, now this will build. So now my ADC is driving the LEDs. So the ADC is probing at 100 kilosamples. God fucking damn it, son of a bitch. Oh, here we go. Okay. Okay, so we're trying to make this PLL. Capture me. Okay. FPGA clock 50. I don't think I use this anymore. There's some cleanup I can do here, but just want to make sure this builds. But yeah, I think this is going to work, man. You can use this headless. Yeah, it's all tickle. Yeah. Yeah, I know. I know. But yeah, I mean, ultimately, none of this was too bad. You have to like know what you want to do. That's kind of the hard part, but like, I don't know. I feel like I could just add this to my project pretty easily now. It's like you open the fucking platform designer, you add the like system sock, you add the bus, we put the slave on the bus, and then that makes a master that we can put slave devices on, and then just hook all that shit up. Pretty easy. Where do you want to go out, Bubbo? Did it build? Look at that. It built. Okay. So, yeah, I should be able to flash this. Right, we'll send this down to the device. And now I should have my ADC working. Yep, ADC is working. And now I just need to bang that ADC output into this, add or some export, right? Right? Out ADC on chip select. So if there's new data, then assign add or some output from out ADC, right? So literally when new data is available, just save it. I think that will 0 extend it. I'm not 100% sure. Must have a variable data type. Object wire out ADC. Wire. Sample. Oh, do I have to assign that because it's a wire? So let's do 63. And then we'll do sample gets assigned out ADC. And then we'll just do assign the sum export is equal to sample. I think that's all it is. I don't know if that's going to sign extend it. Because out ADC is 13-bit signed. I don't know if this will sign extend it. Sample is also marked signed. But yeah, out ADC is signed, so it should know that that's signed. So I think it would sign extend. Would be my guess. So if it's not reset, then sample, that's going to store sample, and then the adder sum is the sample, and thus, yeah, I guess that's where it's connected. So when we read CO10, we're going to get a 64-bit, which is obviously overkill, but we're going to get a 64-bit ADC sample. That would be my interpretation. And it's cool because all of this allows us to dynamically program it. We don't have to constantly keep like rebooting the system and changing the DTB and all that sort of stuff. So like the kernel will just stay booted forever. Okay, let's just start working on this program then. So for loop printf %d %lld pointer res sleep 1. Beautiful. Fuck. Dude, how do I get Control-C to work? Well, I gotta reboot the system. Yeah, how do we get fucking Control C to work? Okay. Okay, let's program this. Now we have the ADC. Yep, so the ADC is working. And then we just have to do the ADC conversion. Let's just do an int. Int val is equal to pointer res. So we'll truncate that. And then we'll do val shift left equals, we're gonna shift it by 32 minus 13. Right? And then val shift right equal 32 minus 13. That's gonna do a 13-bit sign extension, correct? And then we'll have val here. And then let's just break. Six. Sounds reasonable. Let me hold down, if I hold down reset, negative 4096. That's the reset position. Let's go! Yeah, that's the reset. Sets it to max negative, which is that. Okay, so now we can do our ADC conversion, which is double voltage is equal to val divided by 4096. Yes. Val divided by 4096 times 3.3, which is the reference voltage. Printing double, is it LF for double? Okay, if I hold reset, negative 3.3, which is the min. Okay, so now we can read the voltage off that ADC, which is getting sampled a million times a second. And now, the scale, the linear scale, I actually, the wire is damaged on it. I need to put a different reader wire on it, so I have to resolder that board. That's going to take some time offline. But what I can do is I can hook up, I can temporarily hook up a power supply to the ADC. Okay. 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 This. Okay, so the ADC should be pretty unstable right now. I haven't turned on output. Output on. 1.508, let's go! I have the power supply set to 1.5. 1.500. Look at that. Let's fucking go. So in theory, I'm getting a shit ton of data here. I wonder how accurately I can use sleep. What's 100,000? You sleep 10? You sleep 10? Int data is equal to calc 1. And then we'll do size of int times 100,000. Or how the latency of the read is? Yeah, I have no idea. In reality, I'd want to do like memory buffer, like ring buffer into memory. But for now, this is something. In reality, I could actually stamp these with a time, like an incremental counter, and I could see like, can I actually observe all of the sequential counts on the Linux side of things. Okay, and then we'll do int records. Okay, records, int I is equal to 0, I is less than records, I plus plus, and then we're gonna do data I is equal to val, right? So that's gonna sample all 100. Oops. This is going to sample 100,000 data points, right? Should take about a second to run. Nope. Fuck. So the answer is definitely no, can't sample it that fast. It could also be the sleep. We could just get rid of the sleep at this point. Let's see what happens. Whoa. Is the use sleep granularity just bad? Okay. Maybe it's pretty fast if it's actually doing those reads. Unless that all got optimized out, which maybe it did. But with the sleep, it couldn't optimize it out because there's a syscall. So let's at the end do a file fd is fopen log.bin, write binary fright of data 1 size of int times records into fd and close fd and size t bytes written, and then if bw is not equal to size of int times records, then pair fright error return -1. Okay, hopefully we can just do that in one shot. FDD. Okay. That looks like data. Can't control C it. How long is this gonna take? I think we're just gonna reset the system here. Okay, let's do okay, do I just do a usleep 1? No. Okay. I mean, it's still a good smattering of samples. So we have 100,000 records. So we're missing like a sixth or like 5/6 of the data. But that's okay. It's not too bad. Uh-oh. How do I send this file down? How hard is it to start SSHD? What would the SSHD server be? Is it the bear one? Oh, fuck. Isn't it bear? And see that data? I was thinking about that. It just sucks. DDIF is equal to log.bin. And then you and then we're gonna pipe this to NC 192.168.1.2 6969. I think I was doing this the other day. Sudo you have to status 555. NCL 555. Is that not how that works? No, that worked. Okay. Then we'll drop this to log.bin. Okay. We did it. We got data. Plot. Set format binary %d. Plot log.bin using one with line. Oh, how do I GNU plot binary format? Give me an example. I want an example. Format equals int skippity toilet and beep 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 skip-bop Buddha. I think I need to do this first with line using one. Skibbity pause -1. We have data. Okay. Yeah, relax. Set term QT size 1440 by 900 set grid. And then we're gonna plot 1 divided by 4096 times 3.3. Set Y label voltage. Set X label sample number. There we go. That is 1.5 volts. Okay. Now, let's change our program. Okay, let's sleep for... Let's do 10,000 records. And we want to do 10 seconds. So we want to do 1 millisecond. 1 millisecond per read. This will take 10 seconds for this program to run. And then I'm going to fidget with the voltage on the power supply by 0.1 volts at a time. Okay? So here we go. A dot out. And then I'm going to go down, 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 down. Let's go to 0. Okay. Okay. Uh-huh. Yeah, uh-huh. Okay. Hey, look at that! So it's starting at 1.5, and then that's me clicking down 0.1 at a time. 13-bit ADC, 5 bits of noise. I mean, it's on a breadboard. And the reference voltage is probably not great. Do you want me to give it a better reference voltage? Do you think that's what it is? Yeah, let's take a look at that. Desu wants to see how much noise there is. How much noise is there? We're a noisy bunch and got a brunch and we got what codes are we getting here? A range is like 1878 to 1855. Is that what I said? So 23, log 2, 23. Yeah, like 5 bits of noise. I think that's probably just the voltage reference. You want me to check? Let me try and give it a better voltage ref. And I'll set up sense lines too. Fuck you, Desu. You little slut. Be right back. Mumbo, you want to come in? Hey, S'mores. You a good boy. Yeah. Okay, so... Okay. So... Okay. Turn off the output. Okay. reference. Okay, so channel 3 voltage. 3.3 current. 10 milliamp. Okay, 3.3 volt reference. And then we'll set up even sense lines. Sense. Okay, so now I have a 3.3 volt supply, and I even put in the current sense lines for the reference voltage. I should also put in sense lines for the supply voltage. So let me go put that in too. I need one more banana connector, and I don't have it. How many am I using? I gotta have more. 4. What is it? What do you see? Oh, there's people out there. Hi. Hey. Hey. No barking, Bubble. It's okay. Hey. Woof. Where's my last connector, chat? Okay, I made my own cable. Now this is going to where this goes, which is here. Okay. Okay, so now, in theory, we have a much better reference voltage. Okay. So now we're going to do the same program, and I'm going to sweep up. I'm going to sweep up from 0 volts. So we'll start it. Okay. Up, 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 up. Okay. I'm actually going to do this again. I'm going to start it at 3 volts. And then I'm going to sweep down pretty fast. Okay, here we go. Saving. That's 1.5. 0.5. 0. Okay. Hi, Bobo. Let's see what happens now. I don't know how accurate this power supply is, but I imagine it's way better than whatever's on the FPGA board and like going through different current draws. Is that a bigger range now? Okay, it's noisier. Yeah, I mean it really is just a matter of the noise is really just a function of the quality of the voltage reference. I wonder if putting some resistance on here would help as well. I'm not 100% sure what this ADC wants for like a pre-filter. But yeah, it's also on a breadboard, so like there's only so much you're gonna get off a breadboard because there's gonna be so much capacitance on this board. But yeah, I mean we're within like it's really hard to say like is this noise from the power supply? Unfortunately I don't have my multimeter here, so I can't easily check that, but like this could just be noise of the power supply because it is a high current power supply. To get a really good voltage reference, it's not easy. But yeah, plus minus 50 millivolts. That's a lot. It's not the photo detector. This isn't hooked up to the scale. But yeah, I mean, this is clearly working great. I'm pretty happy with this. Whoa, are we getting exactly 10 seconds? I think we are. I think this is actually... I think our sleep 1 millisecond works. But yeah, in reality, I'm going to want to like buffer this stuff and transfer it. Yeah. I can see what my handheld multimeter says. My handheld multimeter is saying 3.30... 3.301. Yeah, and 1.8998. So I feel like the power supply is quite stable. This is just 1.9 volts, the entire test. But yeah, I don't know how much it matters for the supply of the actual ADC to be stable. Because that's still just running off the FPGA 5-volt pin. But ultimately, running ADCs tight here is not, like, running an ADC accurately is not trivial. What? What? Is it... Is it just... What's going on here? Probing? Is it just stable now? I did have s'mores, like, licking the power supply when I did that last one. Let's see, though. But I'm getting Fs. It's not this. Empty range. It should be 1.9 volts. Yeah, something's not operating on the ADC. The ADC was not fully in the board. The ADC was just like hanging out. Okay. Okay. It's at 1.7 volts. .7 volts. Come on. Let's see what we get now. Maybe it just wasn't in the board, but I think it's going to be the same. Yeah. Yep. I'm just getting kind of like plus minus 50. In reality, it's probably more like plus minus 40 millivolts. Plus... And how big is plus minus 40 millivolts? So let's say 80 millivolts over 6.6 volts. Like 1.2% error. Let me put a resistor box in the path of the voltage. Okay. Sense. Need a jumper. Hi, Bubble. Okay. And we'll go here. Into here. Yeah, I haven't really read the manual on like whether or not to do like pull-ups or pull-downs on some of these inputs to like clear them out. But we'll see. Let's just do. So now it's going through a 100k ohm resistor for the input voltage. I don't understand how that would actually affect anything. I guess in conjunction with the capacitance of the board, maybe it does something. But really, a solderless breadboard is just going to be really noisy. Like, I just don't think you can do too much on a solderless breadboard. Either buffer or add a cap on the input for DC measurements. Yeah. Yeah, that had no effect. Not surprised. I don't know. It's something that I'd have to play around with. But ultimately, we have a way of getting information from the FPGA to the sock. So now I can just add more ADCs. So I'm going to add probably a couple more ADCs, output their data together, make maybe like a little ring buffery boy. Yeah, that's kind of the plan. So I got what I wanted to get done today. I wish this was directly writing to memory, but I think this is probably gonna be good enough. I'm not sure. I'm not sure if I can pull this. Like, if I made, like, a couple more registers of buffers, I wonder if I'm going to drop any values reading it in memory. Obviously, I just want to push it directly to memory, but for now, this is a fun little intermediate step, and this is going to let me start playing around with the scales, recording the data. So this is really what matters right now the most, in my opinion, because what I want to do is get the raw data out of the ADC in every incremental step such that I have the same stream that the FPGA would have to work with, and then write some like Python scripts to process the signals until I come up with a strategy that seems to work well for processing the signals. And then once I have a good strategy, then I'll implement that strategy in the FPGA, and then I don't actually need to get like the real-time data. over into Linux. Like, Linux doesn't actually need to stream this data. What we have now, where I'm just getting that voltage and then I could stream like a count, I think that this interface right now should be totally sufficient for what I want to do. To the point that I just don't think I'm going to do the memory writing stuff, because in reality, I'm just not actually going to need to directly stream the output. Pulling it's not great. Like, streaming it's nice for doing processing and stuff, but ultimately I really only need to read this like 60 times a second to update the display. So anyways, I'm really happy with this. I'm glad that Linux just gets to stay up and running and I can just change out the FPGA code on the fly. That's really cool. So yeah, I'm happy with this. I gotta go get some food. I am so hungry right now, and take s'mores out for some fun. But yeah, thanks for stopping by. I hope you had fun. This was quite a lot of viewers. I'm surprised. Don't forget to hit the follow button if you want to catch streams like this if I ever stream again. But yeah, the follows really help more people show up, and when people show up, it's easier to stream. So don't forget to follow. So see you around. Oh yeah, we need to host someone, right? I always forget to do that. Who are we gonna send you to? Who are we gonna send you to? I don't like fucking watch any Twitch right now. Code Miko still streams? Are you uploading the VODs? Yeah, if I'm not lazy. I should, and it's fucking easy with my internet, but where are we sending you guys? Where's science and technology? Where the fuck is science and technology? You're programming and development? Okay, is anyone doing stuff? Holy shit, is nobody streaming this? Oh, it's not sorted by viewers. Okay, who's doing cool stuff? Science and technology? Does anyone do science and technology anymore? I don't think you're supposed to, right? Unless you're doing science and technology. Yeah, those are all science nerds. Okay. Everyone does fucking Unity. Furries, of course. Fucking furries. I don't know, like, any of these streamers. I don't know any of them. Everyone just does game dev. Man, people love game dev. I've just never gotten into game dev. Like generation 6502 assembly? The fuck is this? Sure, 6502 assembly. We're gonna send you to this dude. Wait, are they speaking English? Yeah, apparently. This? How do I, like, raid them? Do I have to select it? Do I have to slash raid? Shit. Yeah, this dude's a fucking turbo nerd. Look at this guy. Look at this Unix-ass beard. Slash raid? Channel? Okay, get the fuck out of here.